welcome to the all present. My name is Maria Fernanda. I civil engineering for the Universidad of Antioquia. Today we continue with the Conference of Scientists Evaluation of Landslide 2022 Landslide Hazard. We hope you enjoyed and learn from each of the research papers that we represent. I remind you that you can leave your question through each of the platforms with our conference broadcasts. Today we'll start with Dr. Amir Shefi with his research paper entitled Probabilistic and 80,000 square meters landslide in Charis, Iran. Dr. Amir will tell us more about this affiliation work.
Well, thank you very much. First of all, I should say hello to all. I think that for those from Colombia, I should say good morning. And I thank Dr. Roberto Marin and his colleagues for giving this opportunity to me. The title of my presentation is Probabilistic Analysis of an 80,000 square meter landslide in Shiraz, which is a city in Iran. And this is not a work just by mine alone. I had some colleagues, Dr. Falomaki, Dr. Ali Shafi from California, and one of our master's students, Mr. Farzad Arjmand. First, as an introduction, well, many landslides occur all around the world every year, imposing adverse effects on people, societies, and surrounding environments. And according to a statistical analysis by Petri 2012, at least more than 32,000 people were killed from 2004 to 2010 due to non-seismically triggered landslides, where the landslide causes can be categorized to natural, anthropogenic, and a combination of both. The major natural causes are slope saturation, the seismic activity, and the volcanic activity, and the activities such as excavation at the toe of a slope, adding surcharge to the crest of a slope, changing the drainage patterns, destroying vegetation on hillsides, and construction belastings are among those examples of such human disturbances that could trigger landslides. And according to one of the United Nations manual, UNISDR 2017, unplanned rapid urbanization, poor construction quality, and weak land use management are some of the most significant underlying drivers that increase the level of the risk. And sometimes a combination of both natural and human-induced factors is responsible for triggering landslides. And our research was about a large landslide that occurred in the Shiraz city. You know, it's a district which is called Mansurabad, but the city is called Shiraz. It's a mega city in Iran. Due to the increase in population and development of the city toward the mountains, the potential for landslide has been increased in recent years. The purpose of this study is to conduct a comprehensive study on this landslide so that the basic parameters of shear strength of formation layers containing marlstone and limestone can be determined and compared with field study and back analysis. Well, first of all, I should talk about a bit about the study area. Shiraz is the capital of Fars province in the southwest of Iran with a population of more than 1.5 million. The city is surrounded by folded and fractured mountains composed of sedimentary rocks. And the rapid population growth of Shiraz during the last 3 decades and the lack of land have resulted in construction on hillsides. This migration to higher elevation has significantly changed the environment and geomorphology of these mountains and disturbed the horizon view of the city. In recent years, several landslides have caused a very severe concern. So our study is not the first landslide. We had lots of landslides before too. For example, here on the February 2016, following a moderate rainfall, several marlstone blocks, as you can see in this photo, fell down and blocked a street. Here on July 2018, you can see a landslide occurred. You can see, you can see the slip surfaces here, and this is a residential building. A landslide occurred with and the area covered was about 44,000 square meter. And this is the Psalm 2018. This is a residential building which was built near the mountain slopes. You can see this photo. I took this photo personally from the top. This is the roof of this building, and it was punctured. It was, you can see the roof is punctured due to the rockfall. Several huge rockfalls occurred, and it punctured the roof of this building. And this is a video from the May 2021, where this is a mountainous road in the belt of the Shiraz. Watch this video, please. Well, and in this Google Earth image, you can see the location of recent landslide in the vicinity of the study area. Here, the stars are the location of each landslide. I showed some pictures from July 2018, December, February. And here in this paper, we studied a landslide, a large landslide, which was the largest among all of them, which occurred here. And as you can see, this is the Shiraz. These are the residential buildings, and here this is the mountain, and this is a road, the mountainous road under construction, the road that you viewed in the previous video. So I'm going to talk about this landslide here. On July 15, 2020, a large landslide occurred adjacent to the road construction site and very close to residential buildings. You can see here, this is the residential building, and this is the, you can see these black lines. This is the territory of the landslide that occurred. And it's at the top, it's very, very close to the residential buildings. This is the sliding zone. These are 2 point A and B. We compare two images, one before the landslide, the other one after the landslide, and we saw that the point A moved about 70 meters and point B moved about 90 meters due to this slide. Here, this is the crown of the failure zone. You can see some fractures, some transverse fractures here from the top on the crown. And also you can see here some, white dots here. There are lots of white dots here. These white, dots, these white points are some planting holes that were dug and they were kept empty. Well, according to the local media, 40 homes were evacuated immediately, and fortunately, no injuries and deaths were reported. The area covered by the landslide is estimated to be around 80,000 square meters based on the satellite images, which is the largest landslide in this area. And here, this is a video, I took this video. I'm here at the top of the landslide mass, and at the top of the sliding mass. And you can see here the transverse fractures. Let me play this video. This is at the crown of the sliding mass. You can see parallel fractures. You can see here, this is the road, the mountainous road under construction, which passes through the toe of the sliding mass. Some of these fractures were as deep as 10 meters. So we believe that the depth of the sliding mass was about 10 meters. And you can, here at the top, you can see the residential buildings. Well, and these are, I think, again, another video. Well, I think I should move to the next slide here. This is another video. These are the rock blocks that were moved due to this landslide. And these are the main escarpment that was occurred, that was formed due to this landslide. And again, these are some videos, these are the blocks of the rock blocks which was formed due to this movement. Well, and you can see these are some photos. This is the escarpment that was formed, and these are the the sliding rock masses. And you can see here a bench. We looked at the Google Earth images, and this bench was moved about 229 meters. And this interesting photo is from the toe of the sliding mass. Here we had a ground heave at the toe of the sliding mass. So it was from the crushed marl stones or crushed marls that they heaved about. They had a heave at high as 5 meters at the toe of the sliding mass. Well, the average slope of the sliding zone is about 11 degrees. However, so this is not a very steep slope. It is a mild slope. However, there exists some completely stable slopes with a slope angle of about 28 degrees, just 1 kilometer away from the landslide. In this study, we gathered information and collected data pertaining to the study area. We made several field and laboratory tests, such as the Schmidt-Hammer test, unconfined uniaxial compression test, the XRF and XRD tests. The joints configuration and asperity were measured, and next, all the data were used to model the landslide in a computer program. The limit equilibrium, the limit equilibrium method was utilized to investigate the stability of the slope in a program. Map, you can see the geological characteristics. This red circle is the landslide location. It was occurred in a geological formation which is called the Asmari formation. And this Asmari formation is located in the Iran. We have a very, very famous mountainous belt which is called the Zagros Fold and Truss belt. These are a row of mountains. And this Asmari formation is made up of carbonate formations and quaternary sediments. This formation contains a strata of limestone, dolomitic limestone, random marl layers, numerous tensile and shear joints can be observed around the sliding zone. You can see here, you can see some of these joints here in this figure that due to existence of these joints, the rocks were divided into several blocks. Two sets of perpendicular tensile joints are obvious in the rock mass, which have created relatively regular rock blocks. The space between the joints is filled with soil and weathered materials such as marl and clay. Here in this figure, this is an excavation cut very, very close to the landslide location. Here you can see, I said, two perpendicular joints. These are some near vertical joints, and there was also some horizontal joints. And you can see, for example, here at the middle of these excavation cuts. And here, this is a zoomed photo from the vertical joints. These red lines are the the left boundary and the right boundary of these vertical joints. And this is a pen. You can see that these vertical joints has a width of about 20 centimeter, and they are filled. They had some infilling. They were filled with clay soils and very, very, very highly weathered marls. And this, you can see here in this figure, the variation of marl characteristic with time due to the weathering. At the top right here, A, this is the marl layer, which is a slightly weathered. You can see here, it has just some very few fractures and joints here. Here at the left, B, is this is the same marl layer, but it is at a later time. So it's weathered moderate. You can see that the fractures and the joints are get wider and larger. And here at the time pass, this is a highly weathered marlstone here, and you can see that the marl is really, it's highly weathered, and it's turned into the soil. It's in fact it's a soil, not a marl stone. And this is a side view here. Here this is the crown of the landslide. These are the landslide mass, and the point of this photo is that, as you can see, these are some bedding planes, and we measure the tip of these bedding planes about 15 degrees. And as I said before, the average slope of this, here the average slope was 11 degrees. So we had here the unfavorable layering of the geological layer, and this unfavorable layering had a very, very important role in occurrence of this landslide. And I want to talk about a bit about the climatic characteristics of the region. The landslide occurred in a hot summer day with a maximum temperature of 39 degrees centigrade and no precipitation in preceding 2.5 months. Hence, the water flow has no direct influence on the occurrence of the landslide, but we believe that the variation in the rainfall regime in 2 preceding years has had an unavoidable effect by enhancing the weathering rate. We believe that weathering had a significant impact on occurrence of this landslide. The annual long-term precipitation of Shiraz is about 316 millimeter on average, but in the previous year, that in the 2020, the annual precipitation of about 416 millimeter, which is about 32% higher than the long-term record. And since the materials of the sliding zone mainly consist of soluble carbonate rocks containing lots of joints and cracks, it would be likely that the increase of the amount of rainfall leads to the development and expansion of these joints and provides the geological preliminary of this hazard. In addition, as I said before, and as I showed in the Google Earth image, hundreds of holes have been dug all around the sliding zone for planting purposes in the past few years, with many of them left empty. These holes would accelerate the infiltration rate into the cracks and joints and reduce the shear strength of joints and parent rock. Well, we decided to use the Barton-Bandis failure criterion. It's a famous failure criterion for rocks to model the shear strength of sliding block. This is the failure. This is the equation here. JRC is the joint roughness coefficient. JCS is the joint compressive strength, and phi sub R is the residual friction angle. Barton in 1982 presented a chart for determination of the JRC, the joint roughness coefficient. Here we should, if this is a length of profile, the horizontal axis is the length of profile, and the vertical axis is the amplitude of asperities. You can see here, this is amplitude of asperities. So the geometries of 14 joints were measured in the field, and we used a ruler. A ruler was laid over the joints, and multiple high-quality photos were taken from a side view using a 12-megapixel camera. Then the photos were exported to AutoCAD software, and the joints asperities depth was measured as accurate as possible. Our experience showed us that JRC values include so much uncertainties, and assigning a single value to an 8-hectare area is totally unreasonable. So, we use a probabilistic manner. The average value of JRC was 15.8 with a standard deviation of 4.8. And we also made several tests, both in situ and in laboratory. First, we had a Schmidt-Hammer, the N-type Schmidt-Hammer. So several N-type Schmidt-Hammer tests were performed at 12 locations of the rock mass in the project site. The measured Schmidt-Hammer rebound values, were converted to compressive stress based on the following procedure. First, we convert the Rn, which is the N-type hammer rebound value, to the RL, which is the L-type hammer rebound value, using this equation presented by Aydin and Basu 2005. Next, some of the Schmidt-Hammer tests were performed horizontally, so the value of those tests were converted to downward valley values using the table presented in the paper of Barton and Chubby 1977. Second, we used these two equations. The above equation, it was presented by Deere and Miller 1966, and the bottom equation was presented by Azimian 2017 for Shiraz rocks. Here JCS is the compressive strength and RL is the Schmidt-Hammer, the L-type Schmidt-Hammer number, which was obtained from the previous steps, and gamma is the rock unit first. Furthermore, the 3 uniaxial compressive strength tests were performed on the limestone sample driven from rock cores, and using all this value, we obtained an average value of the uniaxial compressive strength to about 33 megapascal with the standard deviation of about 5 megapascal for the limestone rocks in the study area. And a direct shear test was also performed on the thin weathered marly clay filling. This is the Moore column equation. So these marl clays had the friction angle of 10 degrees and a cohesion of about 20 kilopascal. Determination of strength parameters of marly layers is of great importance because it seems that these layers had influencing effect on the occurrence of the landslide under study. Moreover, the marly layers are found in various regions of Shiraz. For example, here in this photo, this is a highway in Shiraz, and you can see this highway is excavated in marly layers. And this is a very, very, high excavation. The height, I think it's about 20 or 30 meters. So the determination of the characteristics of these marly layers are very, very, very important. We also made some XRF tests. You can see here the results. For example, this is the CaO, calcium oxide. It was included about 50%, and it was also about 40% LOI. LOI stands for loss of ignition, and it can be attributed to the release of carbon dioxide at temperatures up to about 900 degrees. So this XRF results shows that the calcite mineral is an essential mineral in these marly layers. And here the results of XRD test, you can see that in addition to calcite, we had quartz and illite minerals here at this layer. And this is the SEM photo in 2 different scales, and the calcite minerals are obvious in this photo. And then we try to use a numerical modeling. We use the Landslide software, which applies the limit equilibrium method as well as the probabilistic approach used for the stability analysis. So we use the probabilistic approach. So you can see these are the different values of the Barton-Bandis criterion. And here mu is the average value or the mean value, and sigma is the standard deviation. We entered both the mean and the standard deviation in the software. We used 3,000 randomly selected samples in the probabilistic analysis. You can see this is our model. We saw that we had 2 marly interlayers, one at the depth of 2 meters and the other one at the depth of 10 meters. We back analyze. It means that we try to, here, at the landslide, when the deformation are very large, we have a residual state, and at the residual state, the cohesion is equal to 0. So the only parameter that we were seeking was the residual friction of these marl layers. So we back analyze, we changed the residual friction of these marly layers and to find the time, the place where the mean factor of safety is equal to about 1. And you can see here, this is the mean factor of safety of equal to 1. And the resulted value of the residual friction angle for this Marley layer was about 6 degrees, which was about 4 degrees lower than the peak friction angle that was obtained by direct shear test. As I said in the previous slide, in a direct shear test, the value of the peak friction angle was 10 degrees. And this is a sensitivity analysis that we performed. You can see this red line, which is the JRC, has the most significant influence on the factor of safety. And next, these gray lines, the residual friction angle has the most significant impact. And as the conclusion, well, the identification of the physical and mechanical characteristic of the Asmara formation seems crucial, since this formation has various outcrops in the Zagros regions. And owing to the increase in significant landslide in Shiraz in recent years, we believe that the decision makers and stakeholders should take benefit of the expert opinion and consider the safety issues as the first priority. And thank you very much for your attention.
We have no question. Everything was very clear. We thanks Dr. Amichevi for his presentations. Let's wait a minute for the next presentation. We continued with Dr. Ponson with his research paper entitled Probabilistic Hazard Statements of Landslide-Induced River Damming. Dr. Ponson will tell us more about this affiliation and work.
Okay, thank you. Thank you for the introduction. Hello, everyone. Good morning, good afternoon, and maybe good evening. It was my honor to present our work in this conference. My name is Zhen Peng from SKLGP, the University of Technology. Our topic is probabilistic hazard assessment of landslide-induced river damming. And this work is a collaboration with master student Wang Sun, Professor Li Qianbing, and Professor Fan Xunmei. So China is one of the countries with most landslide dam disasters. Two successive landslides occurred in Baige village in 2018, damming the Jinsha River on 2 occasions. It affected a large number of people and caused a huge property loss. Landslide-induced river damming, risk assessment, and management is one of the main means of disaster prevention and mitigation. So the risk of landslide-induced river damming refers to the expected loss caused by the occurrence of potential landslide in the future. It includes 4 probabilities and 1 consequence. They are the probability of the occurrence of the landslide, the probability of a point being submerged, the probability of the elements at risk being at the point, and the vulnerability of the elements at risk. So the probability of raised barrier lake water level exceeding a certain threshold value at a certain point will be discussed here today. It could be an indicator of the hazard of landslide-induced river damming. Landslide-induced river damming hazard assessment involves at least 3 problems we consider. So they are how to quantify the uncertainties, how to determine the input parameters, and how to improve the computational efficiency. So that's the reliability analysis, Bayesian back analysis, and the multi-response triggering surrogate model are introduced here. So our theory is that the past is the key to the future, and our method is from the probabilistic back analysis of past landslides to the probabilistic prediction of future landslide-induced river dam. So first, we construct the landslide runout simulation model based on basal resistance model. It includes 2 key parameters. So they are the friction coefficients and the turbulence coefficients. They are all considered as random variables in this study. So then the model can simulate the runout process of the landslide and output the deposition depth of each point of the landslide. Accurate estimates of the input parameter is the key to reasonably predict the runout behavior of the landslide. So that we calibrate the 2 random variables using Bayesian back analysis based on the observed deposition depth of the past landslide to obtain the posterior distribution of random variables. The key step in this back analysis method is to construct the likelihood function using the observed and simulated deposition depth of the landslide. Then, if a potential landslide is similar to the past landslide, the back analysis results can be used as an indicator for the probabilistic prediction of future landslide-induced river damming. To do that, a performance function here should be constructed, considering the deposition depth and together with the Markov chain Monte-Carlo simulation to estimate the probability of landslide dam height exceeding a given threshold value. Finally, To improve the computational efficiency, the active learning multi-response tricking model is used here to surrogate the original performance function. This model provides an explicit approximation to the runout simulation model, therefore will significantly reduce the computational time. This is the implementation process of our work. So in the beginning, we collect input random variables and the pre and post sliding DIMs of all the LandScient considered. Then update the random variable using the information observed in the first LandScient. Thereafter, the updated random variables are used to conduct the dam height exceedance probability of the second LandScient and validate the accuracy of the proposed method. Meanwhile, the information observed in the second LandScient can be used to further update the random variables and to predict the potential LandScient-induced river damming events in the future. This is a Baige LandScient. It is located on the western back of the Jinsa River between Sichuan and Tibet. And we can see here, this is the LandScient, and this is the dam, and this is the Jinsa River. So we observed two successive LandScient-induced river damming events in 2018. The first dam height is about 36 meters, and the second dam height is about 61 meters. We can see the Polo village upstream. The river was submerged twice. This is the three-dimensional numerical model for the two slides and their performance function respectively. So the prior information of random variables are collected from a worldwide database proposed by Google. Then we can compute their means, standard deviations, distribution type, and correlation coefficients. So we take the first slide as observation. 7 observation points are selected for the first slide. They are located on the border of the deposition area. So using the Bayesian back analysis, the random variables can be updated. We can see that this is the prior information and this is the updated information. So we can see that their means are shifted and their standard deviations are reduced. To conduct the probabilistic prediction of the second slide, we have to construct the surrogate models first. Thousands of surrogate models are constructed, and most of them, of their coefficients of determination are found to be larger than 0.95, which means that the approximation accuracy of the surrogate model is acceptable. Then the probability of raised barrier lake water level exceedance curve, this curve, the red one, can be generated. It is found that the probability of raised barrier lake water level exceeding 60, 65, and 70 meters are about 92%, 73%, and 35% respectively. And also, we can project this exceedance probabilities onto the satellite image. Here we can see this picture. We can see the 3 sigma confidence interval. So and we can see the black line and the purple line. They are the upper and the lower bound of the interval. That means our prediction bound. And here we can see the yellow line. It is the observed zone, and the blue one, it is a theoretical submerged zone. So it is surprised to see that both theoretical and observed results are located in our predicted bound, which implies that the proposed method has a good prediction performance. Then we can conduct sequential Bayesian back analysis and predict the future LandScient-induced river damming events. So first we check the thickness line as observation. And again, to update the random variables using the information observed in the thickness line, here we use 10 observation points, to use their differentiation depth. Using the Bayesian method, the random variables are further updated and their standard deviations are further reduced. This will improve our prediction confidence and provide a reliable hazard assessment results. So we conducted a site investigation of the bike landslide in October 2020 and found two potentially here. This first one, the second one, two potentially unstable rock mass. We name it B1 and B2. Their volumes are about 2 and 7.3 million cubic meters. So we consider three scenarios. They are the failure of each rock mass and their combination. So again, the surrogate models are constructed for the three scenarios to improve the computational efficiency. Here we can see that the performance are acceptable because the green color means a good approximation. Now we can estimate the distribution of rest barrier lake water level and their exceedance curve for the three scenarios, and also to obtain their 3 sigma confidence intervals. The computed results can also be projected onto the centralized image. Here is the result of the scenario 1. The figure on the left shows the barrier lake depth along the river, the purple and the blue one. The figure in the middle shows the potential submerged area in the Bolo village, and the figure on the right shows the details around the Bolo village government. This point is a government building. The blue and the black line shows the 3 sigma confidence interval, and the red line shows the most probable submerged area, as its exceedance probability is 50%. This is the probability prediction results of the thickness scenario, and the figure on the right shows the details, and this is the computed result for the scenario 3. Sorry. And also, we can estimate the 3 sigma confidence intervals for the barrier lake length, the water storage volume, and the number of submerged houses in the Bolo village. The results can be directly used for decision-making of landslide-induced river damming, disaster prevention, and mitigation. So a brief summary, we propose a Bayesian back analysis method to calibrate the input parameter and improve their reliability. We constructed a probability model to evaluate the landslide-reduced river damming hazards. We used the multi-response Kriging surrogate model to improve the computational efficiency. So the computed results can be used for risk assessment and insurance. And also there are many problems should be should be addressed in the future. For instance, to identify the landslide along the river, to determine the volume of the landslide, and to conduct the dam bridge risk assessment. Okay, that's all about our work. Thank you for your attention.
We would like to thank Dr. Fong Song. Thank you for your time.
Yeah, thank you.
Have no questions. Was everything clear?
Yeah.
Thank you.
Thank you very much. Thank you for this opportunity. Yeah.
Let's wait a minute for the next presentations.
Okay, bye-bye.
Bye-bye. Thank you to the attendants. The speaker schedule for this time was unable to attend. We look forward to seeing you at 13 UTC.
All right. Hello, everybody again. We are having some seconds allowing the people coming back to the streaming. We are very happy to continue with the day 3 of the Landslide Scientific Assessment Conference. It is an honor for us to share, to talk with great experts in this topic. We have had magnificent researchers presenting their already published papers and papers published in top scientific journals. And it is the moment of a plenary conference, and I am very happy to present Dr. Massimiliano Bordoni. It is an honor for us. Thank you so much for being here. How are you?
I'm fine, thank you, Roberto. Good afternoon, everyone. Good morning, or everyone's, and I hope you can understand well. And I'm very happy for your invitation. So thank you again.
Thank you. All right. I want to invite everybody to share this link to all those that maybe are going to be interested, because the topic of today, we are sure that will serve to landslide researchers, to students, professors, experts, a lot of people. And I am going to read for you the title of this plenary conference: Prediction of Rainfall in the Shallow Landslides from Field to Satellite. And I want to mention also 2 of the research papers published by Massimiliano Bordoni that we shared to you, and we invite you to download those papers to read them. Development of a data-driven model for spatial and temporal shallow landslide probability of occurrence at catchment scale. This is one of those papers, and the other, observations on soil-atmosphere interactions after long-term monitoring at 2 sample sites subjected to shallow landslide. So you can go to the link we have in the website of the conference, but also so many other research papers published by Dr. Massimiliano Bordoni. So it is an honor for us. Again, thank you so much for being here, and the time is yours. Please, as I asked the other speakers, maybe you can tell us about your affiliation, what are you doing right now in research, or anything about to know you, and you can start.
Okay. Thank you, Roberto, for your introduction, and also to invite me about in this conference, in this interesting conference. And first of all, I just introduce myself. I'm Massimiliano Bordoni. I am a geologist, and I am at the University of Pavia, Department of Earth and Environmental Sciences. And my research activity mainly is focused on slope instabilities that I analyzed from different point of view, from the monitoring, the modeling of the occurrence, the susceptibility and hazard analysis, and also mitigation tools if possible. And I'm also interested on soil hydrology, soil monitoring generally, and also on the realization of geological models at different scales. However, my main activities are related on shallow landslides in particular. And this is the main topic of this presentation. My presentation is focused, in fact, on this particular type of slope instabilities, and on the different methodologies I analyzed and I used, and also I created for their prediction. I want also to mention my colleagues, Dr. Valerio Vivardi and Professor Claudio Mesina, that are my colleagues at the University of Pavia, and we work together into these different topics. So I started first of all introducing the phenomena that I will talk in this presentation, that are rainfall-induced shallow landslides. And the name of these slope instabilities reflects the main features of them. In particular, they are movement of mass of debris, soil, or mixture of them that are induced by rainfall, by rainwater infiltration in the soil. And they have different depths of the sliding surfaces, but generally they are very thin. In fact, different authors identified as maximum depth of the sliding surfaces of these phenomena, generally 2-3 meters in depth, not more. They are able to displace different amounts of sediments, but generally they are little, even if they are able to have a big runout, and this is very important because in this way can interact with different structures and infrastructures, also at high distance respect to the main trigger. Another important feature of this phenomenon is that they are characterized by high density also in little catchments. We can observe tens or also thousands of phenomena in very little catchments. So even if they are little, generally, they are able to displace a big amount of materials. This is also the main reason why these phenomena are very hazardous and can provoke several damages to people, infrastructures, economy, and environment. Another important feature that is important to be figured out, also to define the main methods for their prediction, is the fact that these phenomena are very rapid, are very fast, not only on their triggering, but also on the development and the final part of the displacement. In fact, they can be ranged in the frame of extremely rapid, very rapid, or rapid phenomena. So according to this feature, different approaches can be created and applied to treat this phenomena and to their prediction, but also to the way in order to mitigate the possible effects of them. This is one of the aspects that is debated in recently is if this phenomenon that is very related to the meteorological events, and in particular to the intensity of the rainfall, can be exacerbated or not according to the effect of the climate changes. In fact, there are different, as you can see in this slide, there are different responses about it, but generally, in most of the part of the world, as you can see in particular in America, in Asia, and also in Africa, the rising of the extreme rainfall events induced by this climate change can increase also the probability of occurrence of this phenomena in the most prone areas, and obviously the effects to people and to damages. But the effects of climate change can be related also to the predisposing factors of the phenomena, because shallow slope instabilities are very related and very controlled, for example, by land use, as you will see. Land use and land cover changes induced by human actions, but also by the climate change, can increase or reduce the probability of occurrence of the phenomena, especially in those areas that are more involved on agriculture. Another aspect is related, for example, to the permafrost thaw in high altitude and high latitude zones in which the possibility that could increase the possibility of this triggering in those areas. Obviously, the rainfall and the changes in rainfall regimes along time can also have an effect on the soil hydrological conditions, and in particular on the soil water content and pore water pressure trends. And you will see that these two factors are fundamental to identify the possible moments of triggering of this phenomena. So we have also to face and to analyze if climate change effects can have effect on these soil features and then on the probability of occurrence of the related shallow slope instability. The approach to analyze and to study rainfall-induced shallow landslides, I repeat, is very related and strict to the main features of these phenomena, that are the high velocity of displacements and the high density in small catchments. So the monitoring, prediction, modeling, and mitigation actions towards this phenomena have to be specific according to the different scales of analysis and data availability, but also, I repeat, to the type and to the main features of these landslides. In this presentation, I will show you the approach we developed in these terms. Generally, these approaches are related to a sustainable point of view, in order also to not exacerbate the effect of human actions on soil and on the territories. The first aspect is the monitoring. Well, the monitoring of the rainfall-induced shallow landslides is very peculiar of this type of phenomenon. Respect to other types of landslides that are characterized, for example, by very slow or extremely slow displacements velocities, these phenomena are very fast. We are not able sometimes to analyze the evolution of the phenomenon according, for example, to measure the displacements in field. So the monitoring could be indirect. So the way is to find the meteorological, but also the soil hydrological conditions that could lead to the triggering in the immediate or not future of this phenomenon. This is the method we applied in our test sites, and in particular in an Italian area called Oltrepo Pavese, that is representative of the northern Italian Apennines features, that is very prone to this phenomenon. The monitoring is carried out installing in the soil some sensors that are able to measure the main soil hydrological features, their trends, and the possible conditions that could lead to the triggering of these slope instabilities. One problem is the representativeness of the test sites. Obviously, the monitoring is very hard, as you can see, in wide area in this way, because we need tens of centuries or hundreds of sensors also in small area. So we have to select representative slopes that, for example, are representative from the geological and geomorphological point of view of the steady area, maybe slopes that were affected in past by the same types of phenomena, and also we have to characterize very in details the soils and the materials that are generally involved in this phenomenon. The monitoring of the soil hydrological features is carried out by installing generally in the trench pits on unaffected slopes, unaffected soil profiles, sensors that are able to cover the entire range of measure of soil water content and pore water pressure, and also, if it's possible, soil electrical conductivity and soil temperature. The temporal resolution should be high because they are very fast as phenomena, and for the measure of the pore water pressure, especially for thin soils, it is necessary to couple different sensors able to cover different ranges of measure of pore water pressure. And the main results of this monitoring is the reconstruction of this trend, where you can see the evolution in time, according, for example, to different dry and wet periods, about the water content, saturation degree, or pore water pressure. And obviously, the main aim in terms of slope stability is to identify which conditions are close to saturation or of complete saturation. That is, generally, they are the main predisposing and triggering factors of shallow slope instability. We were lucky in past, even if not lucky because maybe from the cultural point of view, because we were able to monitor effectively a triggering event, the triggering of a shallow landslide, very close to one of these monitoring stations. And in this way, looking at the trends of water content and pore water pressure and electrical conductivity during the triggering event, we found which are the triggering conditions of this phenomenon, this triggering mechanism. This is the example related to our study area. In this case, the triggering mechanism is an uprise of a perched water table from an impermeable barrier here, from topsoils that are less cohesive and then more able to slide. But I want to stress that obviously the triggering conditions, the triggering mechanism could be different according to the different geological, geomorphological, and also environmental settings. But the way to monitor these triggering events should be in the field carried out in a similar way. The field monitoring data can be also used to run slope stability analysis, typically with physically based or simplified slope stability models, as in this case, that are able in particular to model the evolution of the slope safety factor, not only on saturated conditions, but also on unsaturated conditions. Why? Because sometimes at the beginning of a triggering event, the soil is not completely saturated, and to figure out the effective situation and to model in a reliable way the triggering condition, you have to calculate and to evaluate the slope safety factor considering this aspect. So this is an example of application of a model for the simulation of the slope safety factor at the slope scale, and you can see the evolution of the safety factor according to different rainfall events, in particular how safety factor was correctly estimated below 1 in correspondence of the triggering conditions. Another aspect to be considered is that when you want to model in this way at the slope scale, and you know that the soil can have different water retention properties, you have to choose the correct way to estimate the safety factor according to the different water retention properties of a soil. Generally, in fact, you have to analyze and define if it is better to calculate the slope safety factor since water content or since pore water pressure. Typically, if you know that the triggering conditions are related to the formation of a water table and then to nil or positive pore water pressure, it is better to model considering pore water pressure in the slope safety factor calculation. And also, if you have the possibility to monitor not only the drying path of the water retention curve, but also the wet path, it is better to consider the wet one. The monitoring data acquired in field can represent a good starting point for the prediction of this phenomenon, not only using simplified slope stability analysis at slope scale, but also to extend the analysis also at wider areas. We implemented and developed different approaches. One of these is to use a long time series of water content or pore water pressure to reconstruct, to develop model to analyze in time the trend of this feature according to simple meteorological variables in order to create a model able to reproduce the trend of the soil pore water pressure not only on the monitored slope and not only on the monitoring period, but also in wider area and also for other events, maybe in the periods where the monitoring data, the field monitoring data, are not available. And in particular, for example, here I reported an example of a modeled trend of pore water pressure reconstructed by means of a data-driven approach, very simple, using as predictors meteorological variables such as rainfall, air temperature, air humidity, and antecedent saturation conditions to model at daily scale, at daily resolution, the pore water pressure. And you can see that the results are very confident, are very reliable to the real data. And once we defined a reliable model, we could implement it, for example, to predict the soil pore water pressure in correspondence of other events, not monitored in field by sensors, but you can estimate the pore water pressure by means of this model and use this modeled data to figure out the value of the slope safety factor to identify correctly or not real triggering conditions, as in this case. Field monitoring data, long time series of monitoring data, are able also to give you an idea of the trends of the hydrological parameters throughout different seasons, throughout different rainfall events. But in this way, you are able also to implement better physically based models that, as you know, require, in most of the case, initial condition of the soil that sometimes are very hard to be estimated. So by means of monitoring in a representative test site, initial pore water pressure distribution, in this case, you can figure out in a better way and calibrate the pore water pressure trend for different rainfall conditions, and then assessing the slope safety factors also at catchment scale, improving the predictive capability of physically based models, as in this case. Another approach, similar to the previous one, is to use these models, once they are calibrated, to reconstruct physically based thresholds. Rainfall thresholds that are not estimated by a statistical analysis of past events, but implementing the effect of the rainfall and the initial pore water pressure conditions on a physically based model in order to see which events are able to give unstable condition on a representative or on a part of a study area, and then they identify for different pore water pressure conditions which events are able effectively to induce slope instabilities or not. This aspect is very important in my opinion, because obviously the reconstruction of empirical statistical thresholds is more widespread, because all over the world meteorological variables, rainfall in particular, are more adapted and are more measured than pore water pressure, soil water content, and so on. But in particular context, where you know that the effect is not related not only on rainfall, but also on the initial soil conditions, the use of this type of threshold can improve the reliability of the prediction. Another way to predict at catchment or larger scale is to implement data-driven statistical models. You know very well that generally these type of models, these type of methods, are able to estimate susceptibility. So, considering soil, geological, geomorphological, land use feature of an area, they are able to identify which areas, which slopes are more prone to the probability of occurrence of a triggering. But typically, these models are not able to consider the dynamic triggering factors, such as the rainfall conditions or the soil conditions, that are not taken into account, and in this way, you can't estimate also the temporal probability of occurrence, but just the spatial one, the susceptibility. Well, we tried to overcome this limitation, considering in a data-driven method not only the susceptible aspect, so not only considering the geological, the geomorphological, the land use predisposing factors, but also we tried to develop another data-driven model coupled to the susceptibility one to estimate not only the spatial probability of occurrence, but also the temporal one, combining together to give you a map, to give you an information on space, but also on time, on the conditions of triggering. But how can you obtain this type of input data? Because obviously for the predisposing factors could be easier. We have a digital elevation model for the entire Earth. We can obtain land use information for the entire Earth because we have Google Earth, we have some maps, so on. But also information on rainfall, but in particular on the soil hydrological condition, such as soil moisture, for water pressure, not yet. Sometimes they are not available at larger scale from field measure. But a way could be the use of estimated soil moisture condition, for example, from satellite measure. Here there is a list of possibility to retrieve the trend of soil moisture and also of rainfall conditions for all the world at different time and space resolution. And this could represent good proxies to be inserted in a model for the probability of occurrence estimation of shallow landslides. I want to stress you that if it's possible, for rainfall, it's more probable. For soil moisture, less probable. But if it's possible, the evaluation of the best product to be inserted in a data-driven model should be done by means of a comparison between field satellite measures in order to find if the measures collected by satellites are effective on catching the real conditions on field. In this way, you can find also the best product to be inserted in such a model. And this is the example of the application of the method I tried to explain you now. In this way, we can reconstruct a susceptibility map with different significant predisposing factors, but also a temporal probability of occurrence between 0 and 1, also in this case, considering a few parameters, such as different types of cumulated rainfalls and soil moisture conditions, in this case, in the form of saturation degree, acquired in this case by one of the satellite products I showed you before. But if you combine these two information, you can obtain maps, and you can obtain maps that are not static, but dynamic in time, looking at the evolution in time of the stable and unstable areas along a rainfall event, give you an information not only on the spatial instabilities, but also on the days in this case, but you can refine the model also for higher temporal resolution on the temporal probability of occurrence of rainfall-induced shallow landslides. This model is reliable, as you can see, is effective, but it's limited because satellite information are able to retrieve soil moisture for the very, very shallow horizons in the soil, generally for the first 5-7 centimeters in depth, not more. But as you know, the sliding surfaces of a shallow landslide is deeper, 1 meter, more than 1 meter. So in this way, you have to implement, if it's possible, soil moisture information on the depth of the soil where typically shallow landslides could develop. We tried this approach, substituting the soil moisture estimated by satellites with other information, such as reanalysis datasets. So, soil moisture data derived from modeling, hydrological model at world scale, at very big spatial resolution, that can give us the possibility to measure soil moisture not only on shallow horizons, but also more in depth. So we have to identify which are the best combination to model which parameters can be implemented in the temporal probability of occurrence. And in this way, once the data are validated with field observation, also in depth, you can estimate the triggering conditions in time and produce similar maps, but in this case, considering not the probability, not the condition of the soil in the superficial horizons, but more in depth. You can see that the main advantage of considering this type of products is not related to the prediction of the real unstable area, because the true positives rates are very similar to the previous model. But considering information on soil moisture more in depth, in correspondence of the sliding surface depth, can give you better feedbacks, in particular on having not a big amount of overestimation, not a big amount of false positive. That is important, in particular, for the reliability of an early warning system and so on. The last aspect is the mitigation. Well, mitigation is generally of this type of phenomena is generally carried out by typical structural or engineering tools. But if you want to perform a sustainable mitigation way, the best way is to consider the effects of the vegetation. In particular, to figure out which type of land uses of vegetation are able to improve the root cohesion according to the distribution of the root along the soil depth to reduce the probability of occurrence of shallow landslides. This is possible not only on natural or in woodlands, but also on agricultural fields that are managed in different ways. And in this way, you can estimate the evaluation, the development of root reinforcement for different mitigation, for different agricultural management, to obtain the results and to give you indication of the probability of occurrence of landslides for different land uses. This type of mitigation is also effective in maintaining, or if possible, increasing the sustainability of your territory, because this could allow you, in the case, for example, of organic or sustainable agricultural management, to recover abandoned areas, to increase the fertility of the soils and also the soil biodiversity. So, just a few sentences to conclude my presentation and to leave you the possibilities of open questions to develop also your researches. So, as you can see, according to the type of the phenomena, in this case, rainfall-induced shallow landslides, you have to develop and to analyze specific methodologies and tools of monitoring, prediction, and mitigation situation. The monitoring of this phenomena is related not simply to the measure of the displacement of these landslides, but to the continuous monitoring of the factors, soil hydrological and meteorological factors, leading to the activation or reactivation of this phenomena. Susceptibility and hazard assessment is possible at different scales, and you can implement different methodologies according to the scales, but also to a progressive implementation of new data sources, soil moisture, satellite remote sensing, reanalysis products, and so on. After, I repeat, the evaluation, the calibration of these data sets, data sources, through field observations. Mitigation tools and sustainable mitigation tools based on land cover are possible once the most adapted vegetation and natural solution are found. And obviously, we have to analyze more in detail which are the direct and indirect impacts of climate change on the probability of occurrence of this phenomena at different spatial and temporal scales. For example, some of the aspects that have to be analyzed more in detail in the future years. The effects of the burns. Now, many areas are more dry and more affected by burns, which are the effects of the increasing burnt area on the probability of occurrence of rainfall-induced shallow landslides. And on the opposite way, the increase on permafrost thaw at high latitude and high altitude zone. Could this effect increase the slope instabilities or not? I analyzed in this presentation especially the evaluation of the triggering zones, but we have to consider also the runout of this phenomena. And one of the direction of the future researches should be directed to find the methodologies to integrate not only the estimation of the triggering zones, but also to the runout, to the sediment displacements mobilized by this phenomenon. The connectivity between the slope instabilities and mobilized sediment dynamics also to the fluvial, the river network. And also the change in time and space after a particular event induced by this phenomena. Sorry. Okay. And in terms of rainfall thresholds, I discussed now about the typical empirical and physically based thresholds, but since we have more observation on fields and more data sets on soil moisture, saturation degree, and pore water pressure, we have to find ways and methods to reconstruct rainfall hydrometeorological thresholds based not only on rainfall, but also on soil hydrological features. I leave you now some information on projects that we had in past and some projects that are still active, where we are developing these methodologies, and I thank you for your attention.
And me. All right.
Okay.
Thank you so much.
Thank you too.
There is a space for questions. I think even here in Zoom, Dr. Massimiliano Albioli wants to do a question.
No, I'm here. If you want, I can answer you.
May I ask a question then?
Yeah, go ahead.
Ciao Massimiliano, buonasera.
Ciao, Massimiliano.
So I have a simple question. So you worked a lot in study areas in the north of Italy, and the size, as I understand, the size of these study areas is kind of local to catchment scale areas, let's say. And then you show data for a much larger area, even data, satellite data across the whole globe. And my question is it really possible to extend what you describe in your study area where you have, I don't know, I guess higher resolution data? You mentioned global elevation data. For sure you have higher resolution data in your study areas, and so can you comment on this? And also, what's the difference between the results of your monitoring of soil moisture in your study area and the comparison with these soil moisture products, satellite products, I mean? Thank you.
Thank you for the questions. About the first question, well, my answer is related together to both these questions. In my opinion, as I discussed also in my presentation, it is fundamental to validate this data. Because, okay, we have this possibility to give information on for over the world, but this information, if it's possible, have to be validated with field data. Because, for example, I showed you a good comparison between satellite and reanalysis products and the field data, but they are related to particular land uses, to particular land covers. In this case, shrubs and woodlands. But for example, if we refer to other land uses, such as some agricultural areas, this comparison is showed less reliable results. So I want to stress that it's fundamental a preliminary validation and a preliminary evaluation of the effectiveness of the satellite models in terms, in particular, of the temporal trends of soil moisture, but also for the rainfall. Obviously, the method I showed you can be implemented at different scales of analysis according to the availability of data and also to the resolution of the data you have. It is clear that the implementation of a physically based model at regional or larger scale is more difficult than a data-driven, than a statistical approach. So if you want to try to reproduce and to have a good estimation of the temporal and spatial probability of occurrence at regional scale or higher scale or larger scale, if you want, maybe it is better a data-driven technique up to now. Or you have to decide to reduce, for example, the resolution of the spatial input, such as the digital elevation model parameters, if you want to run a physically based model. And also you have, in my opinion, to make some assumptions that could be valid at local scale, where you have a lot of information, but less valid at regional scale. Another thing you have to face is, how can I say, the guidance of the results you wanted to obtain. Because it is obvious, we have to give a balance between the true positive, the false positive, the overestimation, the missing events, and this is fundamental according also to the aims of the committents, the aims of the population, and so on. So the choice of the resolution and the choice of the methods should be also addressed also according to this thing. I hope to have answered you.
Thank you.
You're welcome.
All right, thank you. Let me check if we have more questions in YouTube and Facebook. If you have questions, you can write them right now. Let me read this one. Was the vegetation effect taken into account for the soil moisture?
Well, I didn't present there some data and some analysis we are performing, but we have some projects up to now to discuss the fact not only from the mechanical but also from the hydrological point of view of the vegetation on shallow landslide triggering conditions. It is obvious that the effect of vegetation on hydrological dynamics in the soil is high. And in particular, the higher is the ability of the vegetation to give a higher induced suction, the drier is the soil, and then the less is the probability of occurrence of the shallow landslide. But this dynamic is complex, and we need more information on field, in particular in this case, because, for example, soil moisture products, reanalysis and satellite products are very coarse kilometers, but the land use can change in space every meter, every tenth of meter. So we need to investigate in details on the field this effect, maybe comparing the trends of suction, the trend of water pressure and soil moisture in different land uses according to similar geological factors, geological and geomorphological factors, looking at this effect. We are working on this direction, but we have some preliminary data that they are not so complete to give final conclusions, in my opinion.
All right, thank you. Here we have another question. Which mitigation method is better to protect shallow landslides?
This is a good question. Typically, the shallow landslides are mitigated in different ways, as the other types of slope instabilities, reducing the probability of occurrence or reducing the effects. In my opinion, since this phenomena can be very dense in space, because we can have tens or hundreds of landslides in few square kilometers, implementing traditional engineering techniques are not enough, because you have to spend a lot of money, and you haven't got, I believe, some funds to do it. So it could be better to find methodologies, for example, choosing which land uses are more adapted to improve the root reinforcements on field, and in this way try to reduce or try to reinforce the soil. We saw that this could be very effective, because in natural areas you can choose vegetation that is representative also of your test sites. In agricultural area, in urbanized area, you can choose, for example, to manage the soil in a more sustainable way, implementing those actions that are able to improve the root reinforcement. And if you choose to mitigate through a different type of land cover typologies, this could give you to cover, to extend the mitigation action, not only to some hotspots, but to a larger scale. Anyway, sorry, it is clear that if you have the possibility, engineering technique, walls, gabions, not in this case, but walls, drainage systems, and so on, can be effective at local scale too.
All right, thank you. Thank you so much. Thank you, everyone attending this presentation. Thanks, Massimo and Ordoni.
Thank you to invite me again, and I'm here. I stay here again for sometimes, and if you have any other question, you can write me an email. I can give you my emails, and or you can ask Roberto my email, and we can discuss together about it.
That's great. Thank you so much. Well, it was an honor for us to hear your presentation, and I hope we can see each other again in other academic or event, other space. We can continue learning from you.
Thank you a lot.
All
See
right.
you, and enjoy this conference.
Absolutely. All right. We are going to have some minutes to have a break. We are going to continue with the next presentation. Please check the conference schedule to be aware of the next speakers, the topics, even if you want to download the research papers that were published and we shared. Please visit the conference website, and we will see you soon. All right. Thank you so much for being with us in the Landslide Scientific Assessment Conference. Landslide Hazard, we are very, very happy to enjoy so many great speakers, presentations, research papers, and we are honored to share with those top researchers here. And before we continue with our next presentation and before I introduce the next speaker, I want to remember to all of you, and while you're coming back to the streaming, we invite you to check out the conference website. We just updated with the info about the discussion section, and in some other moments we are going to give the specific instructions, but you can go to the website also to check the conference schedule, and those times all are in UTC, and they are I cannot say that tentative. We are trying to be very accurate with the times, but in some presentations we can have some 5 minutes, 10 minutes more. It has occurred, and even in this occasion we can start the presentation that is that is continuing, or that is the next now. And yeah, we are going to introduce Dr. Stanley Mordensky. I want to invite you also to download the research paper that we shared the link in the conference website and the conference schedule. The title of this research paper is Hydrothermally Induced Edifice Destabilization, the Mechanical Behavior of Rock Mass Surrounding a Shallow Intrusion in Andesitic Lavas, Pinnacle Ridge, Ruapehu, New Zealand. I am sorry if I did not pronounce correctly. And yeah, we have the DOI, the link for getting to the research paper there. So it is my pleasure to introduce Stanley Mordensky. Hello, doctor, how are you? He's going to share with us this moment. Thank you for being here. As I told, or I asked to the other speakers, we would like by yourself to tell us about your affiliation, what are you doing maybe in research right now, everything we can know, any basic thing about you, and then you can start with your presentation.
Sure. So my background in geoscience is a little bit varied. At the moment, I am working for the US Geological Survey, developing machine learning tools to identify locations that are favorable to geothermal or conventional hydrothermal resources. But my background is quite a bit different than this current postdoctoral position that I have with them at the moment. In my PhD research, I was a candidate at the University of Canterbury in Christchurch, New Zealand, where I think the title on the degree, the field on the degree is engineering geology. But really what I was doing was taking engineering geology methods and applying these engineering geology methods in the realm of physical volcanology to understand how hydrothermal alteration changed the permeability and the strength of volcanic edifices. And I should be very clear that the work I'm presenting today has no affiliation with the US Geological Survey. They're quite strict about the work that is produced with their title, or their affiliation goes through an internal review process. And this work has not done that. This work is strictly with the University of Canterbury. So I present to you as an affiliation with the University of Canterbury. And I would be remiss if they didn't get credit for what I'm going to share with you. Just for completeness sake, I'll add that I did my master's research at the University of Oregon in geochemistry and petrology on volcanic systems. I looked at the volatile contents of melt inclusions to understand the magma transport beneath andesitic and basaltic andesitic volcanoes in the Oregon Cascades. And before that, I spent a couple of years mapping metamorphic units on the East Coast of the United States in the Appalachians. So I'm just trying to say that I have a pretty diverse background. It's not that I have only worked in engineering geology, or I've only worked in machine learning. And was there another topic that I haven't addressed that you asked for, Roberto?
No, that's perfect. Thank you again for being here, and you can start with your presentation, please.
Alrighty, let me shuffle some things around and see if I can't do this properly. Let's see, share screen, there we go. Share that. And from the beginning, I'm going to start a timer so I don't run over. All right. So can you see my screen?
Yeah. Perfect.
So thank you for taking the time to listen to my work for my PhD research, and thanks for the invitation. It was a surprise, and I'm always happy to share my work. So I labeled today's talk "The Effects of Hydrothermal Alteration on Deformation in Volcanoes." And really, my PhD research has one unifying message, which, I'm jumping the gun. Let me start by saying that this work was not done in isolation. I worked with a fine range of collaborators. At the University of Canterbury, I worked with Ben Kennedy, Marlene Villeneuve, and Darren Gravely. I also worked with researchers at the University of Strasbourg in France, Mike Heap, Jamie Farquharson, and Terry Ruchley. I also have other collaborative connections with the University of Otago with Rosie Cole, GNS Science in New Zealand, Graham Leonard, and at the Technical University of Munich, Hans Gilg. So this is all to say that this work is it's rather international. It wasn't just done in New Zealand, and it wasn't just done by one group of researchers, but we really spanned many different disciplines. The unifying message from my combined PhD research really addressed how does hydrothermal alteration from shallow magma affect the petrophysical and geomechanical properties of a volcanic edifice. And from that, I took away three key findings. One is that in a volcanic edifice, alteration can introduce new weak rock masses, which contribute to edifice pressurization. Alteration can also inhibit shallow seismicity and may reduce the outgassing potential during deformation. Now that's a loaded 3 points, and that's what we're going to spend the rest of this presentation going into greater detail on. But let me start with where New Zealand is, and forgive me if this is a bit too introductory, but New Zealand is located in the South Pacific, to the east of Australia. And New Zealand consists of two predominant tectonic environments. New Zealand hosts a subduction zone and a translational tectonic environment. Specifically, for the translational tectonic environment, the South Island has the Australian plate sliding against the Pacific plate, and that's what produces the alpine fault and the mountains for which the country is rather famous for. Then we have the subduction zone. The subduction zone is the product of the Pacific plate to the east, subducting beneath the Australian plate to the west. And that creates a volcanic arc. And it's this subduction zone and that volcanic arc that we're going to focus on. And I should add that when you hear about all the earthquakes in New Zealand, New Zealand's quite a mess in terms of hazards, simply because of this unique tectonic blend where you have subduction and translation. And somewhere between these two different regimes of tectonics, you have the plates trying to sort themselves out. As I often say to people unofficially, the countries are ripping itself apart. I don't know of any other place in the world where you have this transition between two tectonic environments. At any rate, I digress. Let's focus on that subduction zone up here in the North Island. Specifically, the subducting Pacific plate produces a volcanic arc that in New Zealand is labeled the TVZ, or the Taupo volcanic zone. The Taupo volcanic zone hosts the vast majority of the active geothermal and volcanic systems in the country. I should also add that the Taupo volcanic zone is a rifting graben. So the Taupo volcanic zone is dropping down as it fills with volcanic material. And this TVZ, this Taupo volcanic zone, is filled with several volcanoes and geothermal systems. For example, this photo on the left is taken from the eastern flank of Ruapehu volcano. This photo is taken from the northern flank of Ruapehu volcano, or facing north-northeast, and we see other volcanoes like Narahoe volcano, also known, if you can forgive me, as Mount Doom in Lord of the Rings, but the indigenous name, the proper name is Narahoe. Behind Narahoe, we have Tongariro, for which all of this land is given the namesake of Tongariro National Park. This is to say that there's more than just Ruapehu in the Taupo volcanic zone. And of course, we have beyond the land, inside the Bay of Plenty, the volcanic arc continues. This photo here is from the eruption of White Island in 2019 that sadly and infamously killed many tourists. And the volcanic arc continues up the Kermadec Trench beyond frame here for at least 1,000 kilometers with the subduction of the Pacific plate beneath the Australian plate. Now, not all the volcanism in New Zealand is found inside the TVZ. This photo, again taken from Ruapehu, is toward the west. The star in the distance is Mount Taranaki, or simply Taranaki. Taranaki on this map is indicated again by this star and is located far in the back arc outside of the Taupo volcanic zone. My research for my PhD focused on Ruapehu. Ruapehu is found in the southernmost extent. It's the southernmost expression of volcanism in the TVZ. Specifically, Ruapehu is an andesitic stratovolcano. Let's start with this photo in the upper right. This is probably one of the better photos of Ruapehu that I have access to that gives you an idea about the general geomorphology and lithological disposition of Ruapehu. Ruapehu is often described as monotonously andesitic. I kid you not, they say monotonously andesitic in the literature. But the compositions can range in some cases to dacite, but admittedly, most of the lava flows of Ruapehu are andesitic. And I should add that most of these structural components of Ruapehu are lava flows 1 to 2, maybe 3 meters thick, interbedded with thin layers of ash and lahar deposit. For the sake of reference, this is Ruapehu in the background here, with Narahoe in the midground, and then a new edifice for this presentation called Red Crater. This is taken from a famous walk in New Zealand called the Alpine Crossing. Back to Ruapehu though. Ruapehu erupts roughly every 20 years, and I emphasize roughly, but the eruptions tend to be rather minor, VEI 3 or 4. In other words, eruptions happen, air traffic gets shut down, but it's not going to devastate the landscape and obliterate the country. These eruptions are explosive, but they're not catastrophically explosive unless you're on the volcano when they happen. Ruapehu volcano has been mapped into 4 lithological units. And I have these units here from Whakapapa as the youngest, down to Teharenga as the oldest. And Teharenga is really the formation that we're going to focus on today. Teharenga is roughly 250,000 years of age, and consequently has been subject to many periods of glaciation. And that glaciation has, in some cases, dissected the original stratigraphy of the lavas that were emplaced by Ruapehu. What that means is that in some cases, I should back up. So what has happened in one case is that glaciation exposed a fossil hydrothermal system. And that's what this photo is of down here. That fossil hydrothermal system is called Pinnacle Ridge by the locals. And at Pinnacle Ridge, you can walk up and put your hand on the crystalline magma chamber that drove hydrothermal fluids or hydrothermal convection inside the system. So this dark triangle is that magma chamber, now crystalline. And then you can walk out the alteration halo for several hundred meters. And at the edge of the alteration halo, you transition from hydrothermally altered andesite to unaltered andesite. What this means from the perspective of a geoscientist, you can walk up and you have this full complex in which you can investigate. So for my PhD, I approached this ridge and tried to sample from as many locations as possible to sample from different lithologies and different distances from the intrusion to try to investigate how that alteration affected the geomechanical properties of the host rock. With that said, the spacing that I collected from was not regular because although not apparent in this photo here, if I can refer you to this photo in the upper right, the topography of Pinnacle Ridge is quite precarious. You can't get everywhere. It's an oversteepened teleslope. And unfortunately, fatalities happen on this ridge every year. So we took caution, and when we couldn't get to some areas due to slope or rockfall, we didn't. Now, when I say geomechanically characterized, what do I mean? Well, I investigated the porosity and the permeability, that is the void space and the fluid flow through that void space in the different samples I collected. Specifically, I investigated the porosity and the permeability of intact sample size or intact samples. Similarly, with those intact samples, I measured the elastic wave velocity, that is the P wave and S wave velocity. Also, I investigated the strength. I did several hundreds, maybe even thousands of strength experiments. This included both uniaxial compressive strength, as well as triaxial deformation using a hook sill. Lastly, because these different attributes that I've mentioned thus far are focused on intact rock, I also looked at the discontinuities. I quantified the discontinuities in the rock masses from which I collected. And by discontinuities, I mean breaks in the rock, like faults and fractures and joints. Using the geological strength index by Hook and Brown, I'm able to assess the frequency, the interactions, the surface conditions of these discontinuities, and apply a number that I can then use for comparison and modeling. From collecting these different samples, I'm running out of time. Shoot, how much? I will speed up a bit, sorry. Okay, so from these different samples that I collected, or from all these different characterizations and samples, I broke the ridge down into 7 geotechnical units, 3 altered and 3 unaltered, specifically altered and unaltered intrusions, altered and unaltered dense coherent lava, altered and unaltered brecciated lava margins. And then I identified a 7th geotechnical unit, hydrothermal vein material. It wasn't great in extent on the volcano, but it was important because it was distinctly different geomechanically than the other geotechnical units. If we compare permeability versus porosity or log of permeability versus uniaxial compressive strength, we see that in general, the data tend to follow a trend across the 7 different geotechnical units. However, the hydrothermal vein material far off that trend line. If we look over here at compressive strength versus log of permeability, we again see that hydrothermal vein material falling off. And that's because the hydrothermal vein material is made of a different mineral composition than the other 6 geotechnical units. The hydrothermal vein material is made of hydrothermal precipitates. So this raises the question of, well, how does that hydrothermal vein material affect the stability of the volcano? From triaxial deformation experiments, I completed the Hook-Brown failure criteria for both intact and rock mass properties of the 7 geotechnical units, and then took all these different parameter data and put these data into finite element modeling or numerical modeling to investigate different scenarios with different degrees of fluid infiltration and hydrothermal vein conditions, such as no hydrothermal vein, vertical vein, and dipping vein, to see how pore pressure changed. And what I found in the current day configuration of Pinnacle Ridge, the hydrothermal vein in vertical and dipping configurations increased the pore pressure of the ridge. Now, with that said, the hydrothermal vein never decreased the strength factor of the current day configuration Pinnacle Ridge beneath 1, and that makes sense. Pinnacle Ridge is standing today. So we tried a different scenario. It's hypothesized that Pinnacle Ridge formed at below 500 meters depth before it was glacially dissected. So we ran the same conditions, but at 500 meters depth. And what we found is that, yes, again, the hydrothermal vein leads toward pressurization, but that pressurization then drops this factor of safety or the strength factor below 1. That is that under these conditions, the ridge has failed irreversibly. So what we find is that a hydrothermal vein can significantly reduce the factor of safety. It not only acts as a fluid barrier due to its lower permeability, but it's weak, and its stiffness is also lower. It localizes deformation and enhances pressure-induced instability. And if I have time, I'm going to briefly run through one last bit, an opportunity that we found while pursuing this study, which was, could we prove that hydrothermal alteration changed the failure mode of the volcanic rock? And what we found, I'm just collecting samples from the ridge. I take a sample back to the lab, I cut it open. And when I cut it open, I find that the rock hosts 2 forms of hydrothermal alteration, advanced argillic and intermediate argillic. They have different mineralogies and different porosities despite having the same protolith. Well, this presented us with an opportunity. Here we have a ceteris paribus condition where the only difference between these samples is the degree of alteration, the type of alteration. So after reviewing the literature, we wanted to identify an effective confining pressure under which one sample would deform ductily and the other sample would deform brittly. And if everything else the same, it would mean that the hydrothermal alteration causes change in deformation behavior. And that's what we found at 10 MPa effective confining pressure. Now, this has massive ramifications. Specifically, this means that, 10 MPa confining pressure is roughly 300 meters depth inside a volcanic edifice. That is much shallower than the previously modeled brittle ductile transition zone at several kilometers depth, or maybe 2 kilometers depth. It's an order of magnitude shallower. Also, the failure mode in ductile rock is often cataclastic pore collapse, and that does not induce a distinct seismic signal like that of brittle fracturing in brittle rocks. If you're relying on a seismic network to monitor a volcano, that cataclastic pore collapse might not be observed despite the increase in pressure in the volcano. You might not get that pre-eruptive signal. Also, ductile deformation often leads to lower permeability and compromises outgassing potential capabilities. The ductile rock high in the volcanic edifice could be contributing to overpressurization of a volcano. And although everything I've described is found in a fossil hydrothermal system on the flank of Ruapehu, the same material is found on top of Ruapehu in an active hydrothermal system. Moreover, these hydrothermally altered rocks from different geophysical surveys, like this aeromagnetic survey from Kurtzy 2020, find that the hydrothermal material extends deep into the volcano. Lastly, this hydrothermally altered rock is not limited to Ruapehu. It's found worldwide, like at White Island. It is heavily hypothesized that the explosion at White Island back in 2019 was partly due to the nature of the hydrothermally altered rock found on the volcano, or in the volcano, I should say. So in conclusion, hydrothermal alteration creates new weak rock masses, which can contribute to edifice pressurization. These new weak rock masses, or the hydrothermal alteration, can inhibit shallow seismicity and may reduce the outgassing potential during deformation. Thank you.
Thank you. Thank you so much for this wonderful presentation. Let's wait for some seconds if the questions that they can write are available for us. It has occurred that because the streaming takes some seconds, I have missed some questions, but while they are probably writing questions, I want to have a question. Give me 1 second. I was reading directly from the paper. And let me, it was very interesting for me that a minor increase in pore pressure is sufficient the slope failure type from deep-seated rotational sliding to extensional rupture in a volcanic edifice, right?
Yes.
The question is how that can be explained. How was that? I mean, what was the evidence to conclude it?
So that's a great point that I didn't even bring up the subject in the interest of time, but okay. So the models show that the pressurization can induce deep-seated failure, and what we find at Ruapehu, I don't have photos prepared, but Ruapehu has a geologic history of mass landslide events. To the northwest of Ruapehu and the east of Ruapehu, you have that classic hummocky terrain indicative of deep-seated landslides or deep-seated volcanic failure. And what this is suggesting is that given the abundance of hydrothermal alteration at Ruapehu, in combination with the mapping that has been completed at Ruapehu, that these deep-seated landslides are occurring, and they're coincidental with the hydrothermal alteration that is found pervasively at Ruapehu. Hydrothermal alteration products are found in these landslides. So in terms of the mechanism that's causing these deep-seated failures, it's hard to, I don't have an answer to that, but all the data are consistent that we have these rotational events.
All right, thank you.
That's a fantastic question. I wish I had photos to share with you, because if you start, I mentioned the Alpine crossing at the very beginning with that photo of Red Crater and Narahoe and Ruapehu in the background. And at the eastern end of that walk, you start walking through hummocky terrain. You're completely surrounded by it. And that's from a landslide from Ruapehu that's believed to have been about 10,000 years ago, but you're several kilometers from Ruapehu. That's how far that landslide traveled. It's believed that Ruapehu has built up and had massive landslides at least on 4 separate occasions in its history.
That's great. That's wonderful. Thank you. Thank you so much. Let me read this question. Do you think this is the case for the rest of the types of alterations? Or for now, it's only for the argillic alteration?
Excellent question. And I hypothesize the answer is that what I presented here is specific to shallow alteration, maybe specific even to simply argillic alteration. But in terms of deep alteration, like let's say propylitic alteration, which is typically happening at much greater depth than the shallower. So argillic alteration is typically shallower than 2 kilometers or even 1 kilometer depth. Propylitic happens at usually deeper than 2 kilometers depth. And that propylitic alteration has a very different effect on the mechanical properties of the rock than the shallow alteration. The propylitic alteration, that often precipitates quartz into these void spaces, into the porosity of the rock. And that infilling of quartz can strengthen the rock and make it behave more brittly. Whereas what I described with the argillic alteration increases the porosity of the rock. There's dissolution that's occurring, and that dissolution is removing rock, creating pore space, weakening the rock, and increasing its susceptibility to ductile deformation under ceteris paribus conditions. Additionally, the advanced argillic alteration replaces those hard silicate minerals with softer clays. And that replacement of things like feldspar and quartz with clays additionally further weakens the rock. So that's a great question. The type of alteration is extremely important. Unfortunately, I didn't have any samples of other alteration that I could use. In fact, that last bit that I shared at the end, which admittedly was from a different study, that was released in 2019, I think. But that propylitic alteration, with its precipitation of quartz is quite different than that of argillic alteration. And I only found intermediate argillic alteration at one place on the entirety of Pinnacle Ridge, and everything else I found was advanced argillic alteration.
All right, thank you so much. Let me read this question. Did you collect all the sample by yourself?
Sometimes I was out there by myself. I did not like being out there by myself. I usually had somebody join me, but I never had a dedicated field hand. I had to make best of the people available to me at the time. Some of these people had never even walked on a trail before, much less across an alpine environment like Pinnacle Ridge. Some of these people were advanced mountaineers, and depending on who was with me that day, I would plan my route accordingly. And Pinnacle Ridge is not a place to tread lightly, or to take without being serious, I should say, because there's one person with me who shouldn't have been with me, and he got seriously hurt while in the field. So it's a place with high consequences.
All right, thanks, and thank you for the question, all those who wrote them. I think there are no more questions. I have to again thank Dr. Stanley for this wonderful presentation, for taking the time for preparing the presentation, everything you shared with us today. It was, or it is an honor for us. I hope we can, in other moment, other event, other opportunity, can talk again. Well, blessings.
Well, thank you so much. Best wishes upon you. If you will excuse me, I'm visiting another part of the country right now, visiting other members of the USGS, so I need to run, but I hope the rest of the conference goes well.
Thanks. No problem. Thank you.
All right,
Blessings.
bye.
All right, we are just in very few minutes with the next presentation. So you can take some seconds to drink water, stretch, I don't know, and see you very soon. All right. Hello, everybody. We are back. So we have those seconds in which all the people is coming back to the streaming, and we are here again, and we continue with another wonderful research that is going to be presented. We have Dr. Andrea Pasqua with us today. Thank you so much for accepting the invitation. And the title of his presentation is Multi-Scale Numerical Models for Debris Flow, from flow barrier interaction to the scale of the event. We invite you to download the research paper we shared of this author and all the other research we have published. How are you, Dr. Pasqua?
Thank you. Everything is fine. Thanks for your invitation. So,
please tell us about your affiliation.
of course, yes, I'm Andrea Pasqua. I'm currently a third-year PhD student at Polytechnic Torino, Italy. Currently, I'm visiting the University of Sheffield in Sheffield, UK. My subject area is debris flow, how to model them, how to carry out numerical analysis of them. We can say that the most of the research I'm carrying out is about how to merge two different approaches to study debris flow, especially 2D and 3D models. I hope you enjoy this presentation. I do my best to be as much as clear as I can. Okay. So as I was saying, this is a presentation about a new method for simulating debris flow with a multi-scale approach. Dr. Alessandro Nardi and I have developed this method at Polytechnic Torino. Recently, Dr. Leonardi moved to Sheffield University of Sheffield, and he keeps working with me from there. I want to start by showing you a recording of debris flow in Swiss in 2005. As you can see in this video, one of the most important characteristics of debris flow is that there are big coarse boulders that tend to accumulate at the front. The second key aspect of debris flows is that although the slope is not very steep, the boulders tend to flow at high speed. The combination of these two factors and the absence of perimetry signals make the evacuation of local population hard to achieve. And thus, debris flow are particularly hazardous. This figure shows an event in Swiss in 2005 in Brienz, in the Alps. The event caused no casualties, but you can see the general destruction due to debris flow. I'm sure you can appreciate that the infrastructure in the valley was interrupted by the event. In Europe, to avoid these damages in areas prone to debris flow, local authorities install mitigation structure, which usually are barriers. I will now address how to design these barriers. Numerical models can be used to design barriers rationally. That average continuum models are the most widely employed to study debris flows. In this slide, you can see a typical realization of that average model. They simplify debris flow by considering the depth average velocity of the flow along the direction perpendicular to the flow itself. Therefore, the number of variables involved is drastically reduced. So debris flow, depth average models are based on two fundamental hypotheses. First, topography is smooth, so no sudden topography variations are present. Second, the velocity is aligned to the flowing direction, so the velocity in the vertical direction can be neglected. The key issue here is if an obstacle or the barrier we are trying to design is in the flow path, the two hypotheses of this method are no longer met. The obstacle or the barrier is a sudden variation of topography, which causes vertical deviation of the flow. Let's now have a look to alternative to depth average models. Dr. Leonardi has developed over many years a method to study the flow-structure interaction rationally. A 3D method based on 3 independent solvers. In blue and orange, a debris flow is represented. The debris flow is divided into 2 fractions. The solid fraction is represented in orange, and it is solved with DEM. DEM study the boulders as spherical particles. DEM feels, we can say that the DEM is suitable for this scenario because they can study very well the frictional behavior, segregation, and so on. The final part is mixed and homogenized with the liquid fraction, which is solved by the 3D lattice-Boltzmann method. The lattice-Boltzmann method is quite a recent fluid solver, and it is easy to cope with DEM. If a barrier is present and it is necessary to study the structural response, the finite element method is employed. I will now show you some application of these models. In this slide, you can see 3 applications of the models. On the left, there is an application with only the solid component of debris flows. It shows the interaction of a dry flow, which is made only of particles, and a rough dam. The second application is on the bottom right, showing only the fluid part of the flow. The flow interacts with an array of baffles. On the top right, both the solid fraction and liquid fraction component interact with a flexible barrier. The barrier is permeable to fluid, while the solid fraction is blocked by the barrier. So let's go back to the case of Brienz. After the debris flow event, some barriers were installed to protect the settlement in the valley. In particular, some flexible barriers and a massive check dam were installed. The problem here is how to apply the 3D model to study this case. It isn't easy because if you want to study this event, you need to simulate a whole mountain, which is the entire mountain. The main issue is that the 3D model, to be precise, needs a very fine grid. In this large domain, it would require massive computational resources. To address this issue, we have come up with a strategy. We take the domain and simulate debris flows with depth average model, which are very convenient in this case because they can solve large domains very quickly. But when the flow approaches the barrier, flow structure interaction is studied just in these areas with a 3D model. So depth average models can simulate a full scale and very efficient. At the same time, the 3D model studies only the flow structure interaction. These strategies merge the pros of depth average and 3D models. Therefore, we are studying the possible advantages of this coupling. For the depth average models, inserting a singularity like a barrier is much more convenient than using an ad hoc numerical solution. For 3D models, it is convenient to be surrounded by depth average models because this is a much more realistic boundary condition than solid walls. The challenge is to find the correct coupling algorithm. The coupling, first of all, the coupling should be two-way. While it is easy to couple 3D and depth average models because you only need to depth average velocities, the other way around is much more difficult because with few information, a whole 3D profile must be rebuilt. Second, depth average and 3D models are based on different constitutive models. Hence, we need to find an equivalent rheology for both the depth average and 3D model. Finally, the 3D model can simulate particles, while depth average models are continuum only. You can see here how we envision our coupling. We take the whole domain, which is mostly simulated by depth average model, and extrude a small area containing the obstacle. This area is solved through the 3D model. When the flow enters the 3D domain, we apply what we call a coupling section. This is where we transform the depth average variables into 3D version. The two models are based on different grids. The depth average model employs a light 2D grid. In contrast, the 3D model employs a much heavier 3D grid. So at the coupling session, we must perform some operations. The first one is an interpolation to convert the velocity held on the 2D triangle grid into velocity on point of a 3D grid. A second operation is to transform a depth average velocity field into full 3D velocity profiles. It is easy to convert 3D velocity profiles into depth average velocity because you only need an integration. But it is much more challenging to do the other way around. So we need to know a velocity profile which is unknown in advance, and the velocity profile is a function of rheology. So we need to talk about rheology. We employ the Moai rheology, which has been developed for dry granular flows. Nowadays, it exists in both depth average and 3D framework. In the depth average case, mu is a function of the flow number, while in the 3D framework, mu is a function of the so-called inertia number. I prefer not to spend much time on details, but I'm sure you can appreciate the similarities between the formulations. Indeed, it is possible to transform from the parameter of one version to the parameters of the other version. Hence, Moai rheology is consistent in both frameworks. Okay. With that said, the main issue now is to convert the depth average velocities into 3D velocity profiles. If we use the depth average model and assume that the flow is on a semi-constant slope, the velocity is constant, and the flow is in a steady state condition, the Moai rheology provides an analytical solution. This solution is the one on this slide. As you can see, the velocity is a function of the flow depth. So this is an actual 3D profile. It is not essential to understand every single term of the equation. Just take note that is a function of the flow depth. If we start from a depth average model, we can integrate the velocity to obtain the depth average velocity. Using some math, we can find the formula to reconstruct the 3D profile from a depth average velocity. This is our prototype to be used at the coupling section. In the next session, I will discuss the first application we have been studying. The first application is a validation through comparison to an experiment conducted by Moriguchi and co-authors in 2009. It is a simple experiment in which some sand is released from a gate, flows on a flume, and then impacts against a barrier. We could simulate the experiment with both depth average and 3D model to simulate the phenomena in its entirety. This is because we are in a very controlled environment and a short flume. The results at the end of simulation in both depth average and 3D models are pretty similar. But during the interaction, please focus on the central frame of the models. The difference between depth average and 3D models are significant. This is because the 3D model, in the case of flow structure interaction, is much more realistic. Let's now move to our copper model. The copper model should study the flow structure interaction with a 3D model, and everything else should be studied with the depth average model. Therefore, we split the flume into two subdomains. The first part of the domain, the one next to the central is simulated with the depth average model. The second part, where the flow structure interaction occurs, is simulated with the 3D model. It is possible to apply the Moire hydrology in both frameworks with equivalent parameters. Therefore, we use a single set of parameters for both models. Finally, I can show you some results. Here, due to the length of the flume, no big reduction of computational time can be really appreciated. But if you imagine a case like the one occurred in Swiss in 2005, the computational reduction would be massive. However, in this case, we were able to make it work. The flow structure interaction is studied with the 3D model, while this part is studied with the depth average model. Of course, this is an undergoing work. We want to apply our approach to much larger scale application. However, we believe both depth average and 3D models are powerful tools which can study different aspects of the flow. So a couple model can take advantages of both of the pros of both models. Of course, the devil is in the details, and some details still need some work. But we hope that in future we will have a model that optimizes the computational time and help to design mitigation structure rationally. Thank you for your attention. If you have any question, I will be happy to answer. Here you can find our contacts and the reference we use to develop our work. Thank you.
All right, we are back again. Sorry for those seconds, and we invite you to write all your questions. I am checking right now the chat in YouTube. I don't see any questions at the moment. Thank you so much, Dr. Andrea Pasqua. Let's have some other seconds to check if we have any questions. I can tell you that this modeling and simulations you are carrying out are not also complex and very necessary. Congratulations, it was the paper you published is also an excellent work. Thank you for those contributions to the scientific community.
Thank you.
All right, yeah, I don't see any questions. Everything was perfectly understood. See you then in other opportunity. I hope we can share in other academic spaces. And we will come back with the next conference in some minutes. Then we invite you to check the conference schedule and we'll be right back.
Okay. Thank you again for the invitation.
Thank you. Thank you. Yes. Hello, everybody. We are back. We have some seconds allowing all the people to come back to the streaming. It is my pleasure to continue with this wonderful event, day 3 of the Landslide Scientific Assessment Conference, Landslide Hazard. And I am honored to be here with two researchers who published this wonderful paper that is going to be presented next. The title of the paper, and we invite you to download it. You can find it in the conference schedule, also in the conference website, the link of the paper. So the title is Predicting and Understanding Landslide Events with Explainable AI, Artificial Intelligence. So it is my pleasure as well to welcome Enrico Collini and Paolo Nessi. Thank you so much for being here. How are you?
Thanks a lot. Thanks a lot for inviting us to participate in your webinar and streaming conference. It is a pleasure for us to present what we have done and what we have published in this paper.
Thank you. It is my pleasure and honor for us having you here. And yeah, please tell us about your affiliation, anything.
Yes, so we are from the University of Florence, and specifically from DISIT Lab. DISIT Lab means Distributed System and Internet Technology, or Distributed Data Intelligence and Technology Lab. We work a lot in the area of smart city and artificial intelligence and big data. I am the chair of the lab, and Enrico Collini is a student, is a PhD student for the national PhD course on artificial intelligence. Okay. So I think that we can start with the first part from Enrico. Please, Enrico.
Okay, so this work was about developing a solution for predicting rainfall-based landslides using explainable artificial intelligent solutions. Landslides are one of the major environmental hazards in the world, and based on these two studies, there is evidence that this is an important problem to assess. Providing accurate predictions, in our case 1 day in advance, could be extremely important for local authorities in order to manage these emergencies. The scenario based of this study is the metropolitan city of Florence, that has 41 municipalities, 1.5 million inhabitants, and the data history on which this work is based covers 341 landslides events. At the state of the art, the majority of solutions provide only susceptibility maps that are static features based, and you can compute them 1 or 2 times maybe per year. And our solution is a more dynamic one and can be used for early warning systems. It can send alerts for the municipalities and also develop dynamic hazard heat maps and can be computed daily. This is the overall architecture of the solution proposed, with the data acquisition, the development of the artificial intelligence prediction models, and also the outcomes that can be displayed in heat maps or alerts to the municipalities. We developed the data of the dataset using a grid composed by 1 kilometer for 1 kilometer square, obtaining this red region of the metropolitan city of Florence, better displayed in this image with the red dots that are the location in which the landslides occurred. And then our solution is innovative because it uses both static features, but also dynamic features like the temperature and the rainfall values. The data are acquired by sensor located in the territory, and these values have been interpolated by using the inverse distance weighting interpolation algorithm. So we compared some of the most used artificial intelligence architectures based on the state of the art in order to provide the prediction for the next day. The resulting best architectures is the X-ring gradient boosting machines that has been trained with almost 9 million data that achieves astonishing results like an accuracy of 0.99 on the prediction of the landslides. Compared to the system that is the Sigma, that is used right now, that was used for the Tuscany region, in which Florence is, that has instead lower values like the false alarm that was really high. Instead, in mode, we can see that our solution is better performing. For the MTS? Okay.
Yes.
So
Yes.
we added the explainability to our artificial intelligence model, and in this you can see which are the most important variables, like the T3, that is the rainfall accumulated in the last 3 days. We used these sharp values to understand more the impact of these features, and in the graph on the right, we can see the impact of the sharp values. The reddish color means that high values of this feature contribute to the prediction of the landslides. As you can see, this one is a really important one. The water level in the soil, that when there is a lot of this, it's probable that it will fire a landslides, or also the free, that if it is not rained a lot in the last 3 days, it is probable that the landslides will not occur. So this is important. High rainfall values associated with also high temperature and high levels of water within the soil have the main correlation with the prediction of landslides events. Our goal was to use these explainable results to develop early warning system. In more details, we also investigated the local event. In this picture, you can see 3 cases, A and B, in which a landslide occurred, and the last one in which the landslides did not occur. These local explanations puts in evidence that which are the features that provided the major contribution to the prediction of the landslides. For example, in the first one, we have the free, max temp SIR, humidity, and in the third one, we can see which values of this sharp contributed majorly to the not prediction of the landslides. This is a better graph to show, because it contains the trend of the sharp values of these features that are the most important ones, and in this date and in this place in which these shock values are based, occurred a landslide. As we can see, we have levels here Hydra that fired a big shock value. Also, day 3 with a big shock values, and this max temps here that fired a high value. So based on these shock values, we can develop early warning system 1 day in advance, provide municipalities with alerts, and also build dynamic hazard heat map. We can say that the solution is robust because in this graph you can see the relation that a particular feature has with these shock values. And in this case, day 30, that is 30 days of rainfall accumulated, when this feature has a value of around 120, the shock value is really high. So in this case, it is probable that it will fire an alert, maybe about a landslide somewhere in the scenario used, studied.
Okay, so as a conclusion, the problem, so we addressed the problem on landslide event prediction, and with the aim of creating an early warning tool for the metropolitan city of Florence, which is an area of 1,500,000 inhabitants and lives. So we used the static land description features and also dynamic features as rainfall, temperature, wind, and so on. Dynamic features just estimated in the last days and in the previous days, but continuously updated every day. So we also tested a large number of artificial intelligence solutions to compare them and to get the best performing architecture. And we identified the XGBoost to be the best for the TSS metric that has been listed in the comparative table before. So regarding the explainable AI, we adopted the Shapley additive explanation, the so-called SHAP, for global and local explanation. Global means to estimate the global relevance, and local to provide at the decision makers for each event the rationale behind the defining condition for the early warning. And most of the case, the responsibility was identified to be assigned to the rain condition in the last 3 days, and the max temperature in the previous day, and the level of water in the river. The most relevant for static features were the precondition for landslide are not so they were identified, while they are not sufficient in creating an early warning system. So to use the landslide, the land features, land static features is not enough to make prediction. It's enough to make a susceptibility map, but not to make prediction. So from the computational point of view, the prediction can be assessed every day for a large area like so with close to 4,000 points is quite viable. It could be computed even for the whole Italy with enough computational capability. So this is much more expensive than estimating the susceptibility map that is typically computed 1 or 2 times per year. And so prediction model can be used to prevent a disaster 1 day in advance, and can be used to inform the population what could happen to create some alarm and early warning. So the paper has been published on IEEE Access this year, so you can get the link from the program and also here. And so is the general idea in our application and in the infrastructure that is called the Snap for City that covers the Florence area and many other areas is to ingest the data, aggregate, perform data analytics, and provide rendering of the many conditions and create a decision support system. So the work has been developed in the context of instrument for the resilience of the risk assessment and resilience of the area, and for providing decision support system. So as in the schema that you see here in the right side, to have a short-term prediction, anomaly detection, and the long-term prediction to provide recommendation and prescriptions that could be used for early warning and for the what-if analysis. The whole infrastructure, as I told you before, is based on Snap for City framework that is a fully open source infrastructure and tools that you can download and install. And they are used by us, but in many cities of Europe, it is also installed and used to make so smart city activities, but also for early warning or just for smart parking, smart light, smart waste, or others application. And also by the European Commission is also used this tool. In the infrastructure, you can have any kind of data, not only the data that we have adopted for the landslide prediction model, but also maps of any kind, synopsis, trajectories, traffic flow, 3D reconstruction, beams, and others. Data. If you are interested, you can go in this link to get a training course for all the experts. You can test the infrastructure. You can free register it on www.snapforcity.org. You can go inside and test and see what you can do. You can download technical documents, flyers, and technical overview of the platform. Thanks a lot for your time and to give us the opportunity to present our work in this prestigious forum. Thanks a lot.
Thank you so much, Enrico and Paolo. It was a wonderful presentation. I noticed it is a great development research, and yeah, it was an honor for us to have you here. I am allowing all the people attending the event that may write the questions they can have. I am checking what streamings. Let me see, we have questions. I don't see any questions yet. Let me ask you something. How was the process of developing programming? Was it part of the abilities or capabilities of Enrico Collini, or in your team it was something that specifically worked other in person? Was it very complicated, or
So Snap for City allows you to develop, to easily acquire data and store them in the Snap for City platform. Then the retrieval of this data is pretty straightforward with the Snap for City platform. The development of the artificial intelligence models has been conducted by me, but in another environment. And then in this Snap for City platform, with the node-RED capability of development, it is possible to include the artificial intelligence model and use them pretty straightforward to develop any kind of dashboard. And so this is really amazing flow of development that this platform allows us researchers to develop a 360-degree solution for a multiple range of problems. This one was for the landslides, but we developed also a lot of smart city-based projects. So if you want to try the development of the artificial intelligence model was made using the Python language, but you can also use in the Snap for City platform R Studio, and yes. Yes, Snap for City platform allow us to conduct useful researches about important problems.
All right, thank you. I notice, or I think that you are very positive about maybe, I don't know, in a future or now to get to predict a landslide or predict landslide. It is what we try to do in early warning systems, what many of us are working right now. How is your perspective about it?
The perspective was that our system needed to be developed also in the Tuscany region because it works quite well for the metropolitan city of Florence. But now we are still managing the business stuff to
extend the application in a larger area, so to the whole Tuscany and maybe to the whole Italy for as a service for the civil protection.
All right, well, then I want to thank you again. And it was very, very great to know all of these things you are developing, what you are working right now. It is very interesting to me, and I am sure that many of the people attending this conference. Thank you for being here.
Thanks a lot.
Thank you. Bye.
All right, we are going to continue with the next presentation. According to the conference schedule, in some minutes we are back. We have this short break and we will see you very soon. All right. We are back again. Thank you so much for being with us. We have had 3 wonderful days. This is the 3rd day of the Landslide Scientific Assessment Conference, Landslide Hazard. We are going to continue with another top researcher. It was an honor, it is an honor for us that Dr. Vittoria Capobianco accepted the invitation, and she's going to present us this conference entitled Recent Innovations in Larimid Risk Mitigation Tool, implementing a novel methodology for expert scoring and extending the database to include nature-based solutions. We invite you to check the paper, download the paper. We share the links, and on the conference website, you can find other information that is going to be useful. Let me say hello to Vittoria Capobianco. Hello, how are you?
I'm fine, thank you. How are you?
I'm great, thank you. All right, as I asked the other speakers, can you please tell us about your affiliation? What are you doing in research right now? Whatever you can tell us to know something about you, and thank you.
Can you hear me well?
Yeah, perfectly.
Okay, great. Okay, thanks first of all for inviting me to present this our recent publication on the journal Landslides. Vittoria Capobianco, I'm currently researcher at the Norwegian Geotechnical Institute in Oslo, Norway. And I have a background in geotechnical engineering with a PhD on the effects of grassroots on the hydromechanical behavior of unsaturated pyroclastic soils. So I've studied how the presence of vegetation in slopes can both change the soil water retention, but also the mechanical behavior of root permeated soils. Right now, my research is still on landslide mitigation measures, looking more at nature-based solutions, which are solutions that use nature and natural materials to prevent soil erosion or to stabilize shallow landslide problems. And I'm involved in several both EU and national research projects. So with the presentation today, I will focus on this Larimid web tool, especially looking at how we have updated the database of mitigation measures with this nature-based solution, and how we have provided this methodology for expert scoring of the candidate mitigation measures. So let's get started. I assume that most of you know that landslide risk is the combination of hazard and consequences, where consequences can be vulnerability and elemented risk. So to reduce the landslide risk, one should either reduce the landslide hazard and or reduce the vulnerability or exposures of elements at risk. So if we look at the framework for landslide risk management provided by Fell et al. In 2005, once we assess the risk, the level of risk, we do some judgments, and we may assess whether this risk is tolerable or not. And if this risk is not tolerable, we need to reduce it. So we either act with non-physical mitigation measures, for example, by using early warning systems, or we may have a decision on risk mitigation options. So the idea of Larimid goes hand in hand with the need to select the most appropriate mitigation option for a specific landslide case. And as you see on the left-hand side of this slide, conventional structural mitigation measures may be grouped in two main categories. We have the active measures, which are aimed at reducing the hazard. So basically, we act on the potentially unstable mass, and we try to reduce the probability of the triggering of that landslide. And here are some examples of active mitigation. On the other hand, we may also act on the consequence side. So by implementing dissipation basins or structures that are aimed at dissipating the energy or containing the mass that is already propagating. So we allow the landslide to take place, but we try to reduce the impacts of the landslide on the elements at risk. So LandRemit stands for Landslide Risk Mitigation Toolbox. I invite you to just scan the QR code or go on the website. It's a free access website. The aim is to provide an extensive database of available landslide mitigation measures. So the landslide experts can look at them and can decide which risk mitigation option is the most suitable for a specific landslide case. And the idea of LandRemit is to assist decision makers for the selection of the most suitable mitigation measure. But also, it acts as a sharing platform for scientists, decision makers, policy actors that not only need to choose a risk mitigation measure based on the technical feasibility, but sometimes there are some other constraints, for example, related to the cost, related to the time of implementation, or the environmental impact of that landslide mitigation measure. So these are the four main questions that LandRemit answers to. The first one is, again, what are the options available? And this is done through an extensive database that you can check out with the description of more than 80 landslide mitigation measures. And then the other questions are they feasible? How expensive they are? What is their environmental impact? And the way LandRemit answers to this question is through scores that are provided by experts in landslide management. So each candidate mitigation measure has scores for different types of criteria that help the users to select what are the most suitable mitigation measure for a specific landslide case. And the way it's built is that there is an analytic hierarchic process that processes the scores provided by users and then gives back in return and lists a ranked list of the most suitable mitigation measures. But I will explain more in detail this how it works later on. So as I said, we have experts and we have users. The experts are those that compile and update the database, and they are and also assign and update the scores to each candidate measure in terms of functional and technical suitability, reliability, feasibility, typical cost and environmental impact. On the other hand, the user may either just check out the database of measures or may provide some information about the site-specific landslide condition. For example, what's the type of movement, material involved, depth of movement and rate of movement, or the surface and groundwater conditions. In addition to that, can give also weight to relevant factors that influence decision-making, which may be timeliness of implementation, environmental suitability, and economic suitability. So Uzzielli et al., which were the developers of the LandRemit in first place within the project Climate 2050, provided this data flow chart just to show what are the main figures behind LandRemit. As I said, the experts provide general scores based on technical suitability and other factors for each candidate measure. On the other hand, the user inputs in some scores for those criteria that are related to the specific type of landslide they are dealing with. And the administrators are just managing the web portal and are those that have built in this analytic hierarchic process for the ranking algorithm. so that the result of the web tool is a ranked list of mitigation measures that the user can check out and see which are those that are most suitable for that specific landslide case. So going back to definition of landslide risk, we group the mitigation measures in two main groups, first of all. So measures reducing the hazards, the blue ones, and measures reducing the consequences. Those reducing the hazards are acting on the triggering, while those reducing the consequences are acting on the runout. And then you see 11 categories. The first two are in green because are the new ones, let's say, are the MBS that we have recently introduced, these nature-based solutions, which I will talk about later. The others are categories which basically group all the mitigation measures that are addressing a specific physical process of a landslide. So, for example, we see category 3 groups all the mitigation measures that are aimed at modifying the slope geometry, or we have some mitigation measures that are aimed at modifying the surface or the groundwater regime, or those aimed at modifying the mechanical characteristics, and so on. So here you see all the categories breaking down. So for each category, we have from 5 to 9 mitigation measures. And the green ones are, again, the nature-based solutions. So let's say that we want to use a mitigation measure for modifying the slope geometry or the mass distribution. Then we may have 6 options. For example, removal of unstable soil rock mass, or substitution of material with a lightweight fill, and so forth. So this is how the database looks like. And right now we have more than 80 mitigation measures updated and available on the database. And here are those for the reducing the consequences. Each mitigation measure has a description, has some pictures taken from examples of applications, has a description of design methods with the relevant references. And at the end of the page, you can just see and look at the scores that were given by experts in landslide management for that specific candidate measure. Recently, in late 2019, we wanted to introduce new mitigation measures by including this new concept of nature-based solutions. So very briefly, nature-based solutions are actions that are aimed to protect, to sustainably manage and restore natural or modified ecosystems that are addressing some societal challenges, but that in the meantime provide also additional co-benefits, for example, benefits to the society or biodiversity benefits. If you look at the societal challenges that are within the framework of nature-based solutions, we have also disaster risk. So nature-based solutions used for landslide risk mitigation can be seen as belonging to this group of nature-based solutions acting on the disaster risk reduction. So the main difference between NBS and other conventional structural measures is that nature-based solutions not only act on the risk reduction, but they may provide also additional co-benefits that can be benefits to the society, for example, improving the quality of life, benefit to the environment by improving the biodiversity, benefits to the local economy by introducing new green jobs, and so forth. So when we talk about nature-based solutions in the framework of landslide risk, most of the time we think about use of vegetation. And use of vegetation or native living plant species or natural materials found locally is called soil and water bioengineering. So it's a technique, is a discipline that is already well known. Probably you're more familiar with this terminology rather than with nature-based solutions, because it's more for engineering, for an engineering point of view. And it's the use of living material, both alone or in combination with inert materials, to construct structures that are aimed at stabilize slopes or reduce the erosion along slopes or river banks. And here is an example of soil and water bioengineering application provided by Stokes et al. In 2014. So you see the slope had a severe problem of surface runoff, surface erosion, and this is the design of the measures. So in reversed Y-shaped drainage system for the hydrological effect, and then some light cuttings put along the slope, as you see in this picture. That may provide also mechanical effects through the roots growing into the first layer of the soil. So here we have an example of how a nature-based solution for landslide application may look like. Recently, we have also tried to we published this opinion paper because we found that there was a bit of confusion of terminologies. So we wanted to clarify how soil and water bioengineering can be seen in light of this new concept of nature-based solution. So we did a recent comparison of terms and definitions, including also other terms that fall under the concept of NBS, such as ecological engineering, ecosystem disaster risk reduction, watershed management. And all of these terminologies were compared with the main aims of soil and water bioengineering discipline. And we concluded that basically soil and water bioengineering is a tool for NBS, can be seen as part of nature-based solution, because nature-based solution is an umbrella concept, as long as we provide some biodiversity benefits. So it's important to clarify that it should not only provide erosion protection or can be used for disaster risk reduction, but should also provide some environmental benefits on top of the risk reduction. So at the end of this study, or this idea of including NBS measures in the Larimit web tool, we also did an extensive literature review of soil and water bioengineering applications for landslide hazard and landslide risk reduction. Also looking at the reports provided by Geotechnical Engineering Office of Hong Kong and the European Federation of Soil and Water Bioengineering. And at the end, we came up with two main categories. The first one was NBS for erosion control living approach, and the other one NBS for erosion control living and not living approach. So for living approach, we mean only natural materials, only vegetation or live cuttings, etc. For a combination of living and not living, we may have also inert materials such as stones or rocks, etc. So here are the mitigation measures that we introduced. For example, hydroseeding, direct planting, or live fascians, or brush layering, live stakes, and etc. And for the second category, we may have also a combination of living material with the geotextiles or drainage blankets and so on. All these measures were also listed and published on this report for the project Climate 2050, in combination also with nature-based solutions for other types of hazards, such as floods, stormwater, erosion, droughts, and etc. So you can just look at this report that we published in 2019. And after we reorganized the database of mitigation measures by introducing these nature-based solutions, we needed to update the scores of the mitigation measures. First of all, because the scores of the existing conventional measures were only based on opinion of a very few experts in landslide management. So they were not robust enough to be used properly. And in second place, we needed to provide new scores for these new nature-based solutions that we have recently introduced. So here you see the timeline of these survey that we sent out to landslide experts, more than 150 landslide experts and MBS experts in late 2019, with a couple of deadlines and then some reiteration to receive more responses, with the aim to update the scores on the website. And we proposed that expert scoring algorithm. I won't go in detail on the expert scoring algorithm, but basically we made this algorithm in such way that we used it once to test out the methodology this time, but it can also be used in future because it's made so that it can be dynamically implemented. So as soon as new expert scoring are coming in, we can just use the expert scoring algorithm and update the scores of the mitigation measure on the website. And it's based on different phases. So we have a data analysis where we calculate the minimum, the maximum, the quartiles of the scores, and then we do some data filtering. Excuse me. Some data weighting, and then at the end we do a score selection and we update it on the website. Here is an overview of the experts that were contacted. I must say that the experts contacted were mostly people in our network and people that were participating to this ongoing project where LandScient was developed. And LandScient was basically meant to be at European level. And that's why most of the experts contacted were from European countries, with some extent to Asia and America. And you can see here the distributions of experts around the countries. And again, here you see most of them were from Italy or Norway, both from affiliation or origins, because the authors and the managers of the website were either affiliated or from Italy or Norway. And here are some results. So you see that at the end, among out of the 153 invited experts, about 25% of them replied, so contributed to scores for at least one mitigation measure. This doesn't mean that only 38 responded. We got only 38 response, but it means that one that responded could respond also to more than one mitigation measure. So at the end, we got a lot of responses for more mitigation measures than 38. And then you see that the majority of responding experts were, excuse me, the majority of responding experts were from Italian or Norwegian affiliations, followed by Spanish, Portuguese, and Chinese, and so on affiliation. Then we asked also the experts to qualify themselves in terms of profession, and about 40% were professors. The remaining 30% were practicing or professional engineers, and then the remaining were MBS experts or researchers, and only 6% were PhD students or postdoc students. Here is just an overview of the number of responses that we got. So on the right-hand side, you see the list of all the AD mitigation measures divided in categories, as I said earlier. And the colors mean MBS, the green ones, gray are the conventional, and purple are the hybrid solutions, which is a combination of both MBS and gray. And you can see that on this other graph, we have an overview of the number of responses for each mitigation measure. So, for example, here, 14 gray measures received less than 2 responses, meaning that we could not apply the statistical pooling, meaning that we could not update the scores because we didn't have enough responses. But for example, for the MBS, most of them received between 3 and 10 responses. So we could apply a statistical pooling and we could update the scores. And only one measure received more than 10 responses. So in total, we received scores for 56 measures that were updated, while the others were not updated. And among these, 21 were nature-based solutions, 3 were hybrid, and 32 were gray solutions. You can look at all these results on our publication on the journal Landslide, where you can see also the discussion about this and how, for example, some mitigation measures receive more responses than others, and so forth. So here I leave you with some final consideration about this Larimit. I briefly introduced the Larimit web tool, how it looks like, how it works, how it's built, and how we updated the database with these MBS measures. And at the end, how we sent the survey, trying to make the database more robust with more scores provided by a larger group of experts in landslide management. But the other idea of Larimit right now, of these recent innovations in Larimit, was also to allow us to disseminate examples of nature-based solutions for landslide mitigation by suggesting a portfolio of possible mitigation measures that engineers may be presented with, they are not familiar with, and may consider for potential landslide cases. So I just want to finish by saying that this project where Larimit was born is Clima 2050 is ending this year, but Larimit will be hosted from 2023 by NGI, with the commitment to support the continuing development of the toolbox. It's an ongoing and it's a work in progress toolbox, because the future activities that we foresee is the addition of expert scoring, improving the underlying engine for selecting the mitigation options, involving also more professionals to fill out the survey, and not at the least to validate the toolbox. Once we will have a large amount of scores, we may validate the toolbox with some examples and some real cases to be applied. So that was my last slide. I'm so sorry for my sudden coughing reaction. I don't know why, but I'm here to answer to questions if you have any, or just comments or whatever. So thanks again for giving me the opportunity to present our work.
Thank you, and thank you for having the presentation, even in probably some issues with your voice or your health. I don't know, but thank you so much for presenting this wonderful thematic. I am going to allow all the people attending the streaming in YouTube to write their questions. I am seeing one question right now, and I also want to ask you something. First, the question here is, I think, let me see completely, sorry. Types of vegetation, I suppose, what are the types of vegetation we need to identify for different soil and different country for nature-based solution?
Yeah. I'm sorry, I'm not able to see the comments, the chat.
Yeah. I can be assume also.
Okay, sorry. Chat. Yeah, okay. By the way, yeah, you asked about the type of vegetation, right? Yeah, okay. Types of vegetation we need to identify for different soil and different country. Yeah, that's a very good question. Indeed, there are a lot of comments provided by nature-based solution experts if you go in the database and you go in some of the mitigation measures that we have introduced for MBS, you may find some specific comments, because it's not easy to generalize when it comes to use of vegetation, because vegetation needs to be local, first of all, so needs to be present in that area already, and it needs to be suitable for the type of soil, and needs to be suitable for the type of climate that we have, and for the available water that we have. So here in LandScient, you may have an overview of the techniques that use vegetation, but to have a good idea of the type of vegetation that should be used for that technique, then you may perhaps consult a botanist or someone that is more expert in the area, because here is just an overview of the techniques that use vegetation for a specific problem, but not which type of vegetation, because that differs from country to country and from area to area and from soil to soil. Yeah, so this information is not available right now on the web tool, but it could be an idea to update it with this information, with the help also of botanists or experts in plant ecologists or experts in the area.
All right, thank you. I have one question. How difficult is the process of collecting the contributions of the experts to answer the questions or the questionnaire? And also how, I mean, in the idea of having a dynamic updating of the scoring, is it possible that, or what, or do you consider that in the time the concepts of the experts are going to vary, so it can be somehow difficult to have a large number of I don't know, answers from experts around that topic?
Yeah, that's a very good question, actually. First of all, I have to say that it was not easy to get responses from Landslide experts, first of all. So we sent out the survey, and as I showed earlier, like the survey was firstly sent in November 2019. Then we gave a first deadline in January, but we didn't get a lot of answers. So we extended the deadline in April 2020, and then we collected the responses. But for some mitigation measures, the responses were not enough. So we sent another survey to a selected group of experts in order to get more opinions, to get more responses. So first of all, it's not easy to gather responses from Landslide experts. Secondly, this was a first tentative, and we basically closed the survey at a certain point that we started to analyze the data, but we left open the possibility to still fill in the survey. So you can just contact me, and I can send you the list of the surveys in Microsoft Forms, so you can fill in the survey wherever you want, and then we aim to update it frequently, let's say once a year. But again, as you said, it's not easy to get. You may get different opinions from different people about the same mitigation measure if the experts come from different parts of the world, because perhaps that mitigation measure in a certain part of the world is costly, or is not used as often as in another country, and so forth. So there are a lot of things to consider when we assess the responses. And I'm not sure about the opinion. So whether a landslide expert may change opinion with time, probably yes, because maybe new solutions are coming up that are more efficient. It's not easy. It should be more dynamic, this LARIMIT toolbox. But so far, it's just updated once a year, and it's not so quickly updated, let's say, with the opinion of experts and so on. But that's a really good comment, actually. Yeah.
Yeah, I agree. It is, but you have to do the best option, and yeah, congratulations for your presentation, your research publication, and thank you again for being here.
Thank you for inviting. Thank you, Roberto.
All right. See you probably in the workshop. I want to ask you also, maybe we can invite all the people to a workshop your institution and you are organizing.
What would you say?
That probably it is a good moment to invite all the people attending this event, to invite them to the workshop you are organizing next year.
We can talk about it. Yeah, we can. Let's get in touch. Keep in touch, and we can see what we can do. Thank you again for inviting.
Thank you.
Yeah, I will just unmute myself and switch off the camera. Bye.
Bye. All right, we are going to continue with the next presentation. We are here with Carolina Segui. It is wonderful to have you here. Hello, Carolina, how are you?
How are you?
Thank you. I am great. Thank you. And thank you for accepting this invitation. It is wonderful for us to have the opportunity of listening from the same researcher, a wonderful research work. We invite all of the participants to check out the conference schedule, the conference or the website of the conference, and we have there also the links to the research papers. You can share your thank you.
Okay.
Continued assessment of landslide by measuring their basal temperature is the title of the paper you published. I want to please share with us or tell us before you start your presentation something about your affiliation, what you do in research, and then you can continue with your presentation.
Okay, thank you. Well, my name is Carolina Segui. I started my research at Duke University in North Carolina with Professor Manolis Bebeakis in landslides. So I graduated in geomechanics. We followed the start of landslide research from the late Professor Ioannis Vardoulakis. And I have been in RWTH in Aachen, Germany, doing postdoc, continuing my research in landslides. And now I am in the University of Barcelona in Spain, also continue my research, but with actually one landslide that I will show you now some what the results and some tests. But we got more core data, core samples, so we are working with that right now.
All right, thank you. Please, you can
Okay.
start your presentation. Take all your time.
Okay. So, hello everyone. Thanks for being here. And thank you, Roberto, again for inviting me. So yeah, I will present one part of my research, which is called continuous assessment of landslides by measuring their basal temperature. I will start with a very short introduction. This is a wall map with a repository of landslides from NASA, where we have here collected over 10,000 landslides that have caused almost 39,000 fatalities in history. So these are the main triggering factors of these landslides. So in general, they seem to be triggered mainly by groundwater level variations, that they are caused by rainfalls or downpour, and also the construction of a dam nearby the area. So now here, this is another study with the projection of losses of different natural hazards, but we'll focus on landslides, which are the main natural hazard that can actually be mitigated by using preventive measures. So, and they rely in our ability to forecast and control the response of the landslide to, as we have said earlier, the external loading, for example, these groundwater variations inside the sliding mass. So now focusing on our work, we work in the type of deep-seated landslides. This is an example of a deep-seated landslide. This is a profile of the case of the Bayonne landslide in Italy that collapsed in 1963. So the main features of these landslides is that first, the rock mass, the sliding mass moves as a rigid block over a thin basal shear band. This shear band or sliding surface is usually below 10-meter depth or below the root of the trees. And these landslides are featured by large slope failure, and they can be translational or rotational depending on the shape of the sliding surface. So they characterize because they move very slowly, so meaning that they are creeping during years or tens of years until they suddenly collapse catastrophically without almost previous warning. So the life of these deep-seated landslides, if I can say that, is presented here. So this diagram shows there's the first primary creep, which is in a very short time, which is the first acceleration of the landslide. Then we have a very long period of secondary creep, which is when the landslide is moving very slowly during years or tens of years. And then finally, there's the tertiary creep, which is the final acceleration and the catastrophic collapse. So to understand the mechanism of failure, why the landslide goes from secondary to tertiary creep, because we need to be clear and say that in the tertiary creep, the landslide cannot be stopped, even taking remediation measures. So
I think we have, and I didn't notice, we have a problem with the window that is shared. Yeah, because it is in the
wait.
In the only. I am sorry.
I don't know. Wait. Let me see. How can I share?
Maybe if you stop trading and.
What am I sharing? This one, right?
Yeah.
Wait, because I have two screens. So let me check.
You can.
Which I can check here. I don't know.
You can close. You can stop sharing.
Yeah.
Yeah, do it again.
Wait, because right now I don't know how to do it. Okay. Let me see. Share screen. This presentation. Share. Can I share it or not? Okay.
Not yet. What you can do is to. Yeah, exactly. It is what you have to do. That now share. Let me see.
No?
No.
Maybe.
Do you have the full
Now?
screen?
Now what do you see?
I don't see the full screen.
You don't see the full screen?
No.
You don't see? What do you see?
I see the PowerPoint. All right, all right. We are very sorry we didn't notice it was happening, but we are going to start the presentation. Carolina very kindly is going to start from the beginning. So thank you, Carolina.
Yeah, thank you, and apologies for the technical issues. So yeah, hello, thank you everyone. My name is Carolina Seguí, and today I will present you part of my research, which I did with my supervisor, my thesis supervisor, Professor Manolis Bedeakis, continuing the work of the late Professor Ioannis Vardoulakis. So, which is called continuous assessment of landslides by measuring their basal temperature. So I will do a short introduction. So here we can see a wall map, which is a repository from NASA of all the landslides recorded that have been recorded in history, which are over 10,000 landslides. And from all of them, they have caused over 38,000 fatalities. So the main triggering factors of these landslides is mainly around 70% is triggered by groundwater level variations due to rainfall or, for example, dam construction nearby. So this is another study that of the projection of losses from natural hazards, and what we obtain, what we get here is that actually the landslides are the ones that can actually be mitigated if we use preventive measures. So these rely on our ability to forecast and control the response of the landslide to the external loading, as I said before, these groundwater variations. So now introducing our work, we focus only on deep-seated landslides. This is an example of a deep-seated landslide. This is the one profile of the Bayonne landslide that collapsed in 1963 in northern Italy. So the main features of deep-seated landslides are first that the sliding mass moves as a rigid block over a thin basal shear band or sliding surface, which is located usually below 10-meter depth or below the roots of the trees. And it can be up to hundreds of meters depth. So these type of landslides can be rotational or translational, depending on the shape of the sliding mass, on the shear band. And the main feature of these landslides is they have a large phase of very slow movement, which is called creeping, during years or tens of years until they suddenly collapse catastrophically. So this diagram shows the life of a deep-seated landslide, if I can say that. So first, there's a short period of primary creep, which is when the landslide starts accelerating. Then there's the largest period here in the middle, which is the secondary creep, where the landslide moves very, very slowly during years or tens of years. And finally, there's the tertiary creep, which is the last part, which is the last acceleration and the catastrophic collapse. It is very important to say that once the landslide enters in the phase of tertiary creep, even if we take remediation measures, the landslide cannot be stopped. So to understand better the mechanism of why the landslide turns to secondary to tertiary creep, we focus on the critical parts of the deep-seated landslide. The first one is the eroding toe. For example, if we have a river, it removes mass from the toe, which is the stabilizing part of the landslide. Then there's the deforming shear band, where all the kinematics happen, and then the groundwater level variations inside the sliding mass that gives extra loading to the shear band. So in our work, we will focus on the deforming shear band and the groundwater variations inside the sliding mass. It's important to understand that these deep-seated landslides are very violent and catastrophic. And I remind you again that once they enter the tertiary creep, they cannot be stopped even if we take remediation measures. So now I will explain you the mathematical model we use that we couple the external loading, so the groundwater variations, with the internal response. So how the material of the shear band behaves, which we have called the Bardulakis forecasting model in honor to the late Professor Ioannis Bardulakis. So this model has this mathematical model has three conceptual models of the landslide. The first one is a 2D profile of the landslide, where we perform a limit equilibrium. In this case, it's a two-wedge method for simplicity, because the goal is to calculate the shear stress of the entire part of the landslide with different groundwater levels inside the sliding mass. So once we obtain this shear stress, we convert it to an infinite rigid elastic block for simplicity for the model, where the stresses calculated from the model A are admitted in the basal shear band, which is our conceptual model C, where we can see the velocity profile along the vertical profile of the vertical section of the shear band, and also the evolution of the temperature along the shear band. So now moving into the mathematical model, we will focus now on the behavior of clays, because most of these deep-seated landslides, their shear band is formed by clays or clay-like materials. And Professor Bardulakis postulated that clays, they consider that clays are fully saturated in water, perfect viscoplastic material, and that they are velocity hardening, meaning that when you increase the strain rate, or your shear stress increases. And they are also thermal softening, meaning that when the temperature increases in the material due to the friction, because of the acceleration of the landslide, your friction coefficient of the material decreases. Therefore, the velocity hardening is a power law, where at the exponential, this n is the rate sensitivity of the material, and the thermal softening is an exponential law with m, that is the thermal sensitivity of the material, theta is temperature, and theta1 is a reference temperature from the field. So Professor Bardulakis ended up with an equation of the friction coefficient at critical state that combines velocity hardening and thermal softening. So now moving forward with the mathematical model, with this viscoplastic shear band, we take as a constitutive equations the shear strain rate, that considers the shear stress, the rate, the strain rate, the rate sensitivity, and the ratio of thermal and rate sensitivity and the temperature. We also take the general form of heat diffusion equation, and we also perform a momentum balance for clay, where in the horizontal direction is driven by the shear stress, and in the vertical direction by the normal force. So what our goal is to study the stability of these deep-seated landslides. To study the stability, to see if we are in the second, so in the phase of secondary creep or in tertiary creep, we take the heat diffusion equation I just showed you, and we pass it to dimensionless form for simplicity, where this equation depends on two parameters, the Grunfeld number and the temperature at the exponential. This Grunfeld number is a dimensionless number that takes into account all the values from the material of the shear band, and ds is the thickness of the shear band, and also the external loading that we calculated in our conceptual model A. So now to study the stability, we take this heat diffusion equation in dimensionless form to a steady state, so equal to 0, and with applying the pseudo arc length continuation method, we obtain this steady state curve or Bratu curve, where we plot the Grunfeld number and temperature in time of the landslide, which is equal to the external loading with the shear band temperature. So how we interpret this, this curve? So here we have the peak of the steady state curve and the maximum value of Grunfeld number, which can be stable. And then if, for example, in our landslide, the Grunfeld and the temperature are within the gray area, the lower branch of the steady state curve behaves as an attractor and the landslide is stable. However, if the Grunfeld and temperature are go outside this gray area, the landslide is in tertiary creep, meaning that the landslide catastrophically collapses. Therefore, our goal is to maintain the behavior of the landslide with the Grunfeld number and temperature within the gray area. So now we want to test the mathematical model and also the effect of the temperature playing an important role in the stability of the landslide. So we took a field case study, which is called El Forn landslide. This landslide is located in the southwest of Europe, in a very small country between Spain and France that is called Andorra. This landslide, you can see here, very large landslide, is about 300 million of cubic meter of rock mass that is sliding towards the city of Canillo. But inside this large landslide, there's a small lobe around 1 million of cubic meter of rock mass that slides faster. And here we can see from the S10 borehole that has been instrumented the inclinometer data of this lobe, where we can see that it moves as a rigid plot, meaning that is a deep-seated landslide, and the shear band is between 29 and 29.5 meter depth. So the material of this lobe is mainly formed by black shales and limestone of the Silurian period. And here we have the core samples that we have tested in the laboratory, and where we have found apart from the inclinometer data in the experimental test that I will show later, that the shear band is between 29 and 29.5 meter depth. Now, here is an example of the remolding of the samples and the final shape of these samples for testing them in the thermal triaxial. It is important to note that we have divided the depths of the samples at each half a meter. So we perform an experimental campaign in a customized thermal triaxial machine that we have at Duke University. And these are, because they are core samples, the material is very limited. So we did exactly the same test for all the samples outside and inside the shear band, because we wanted to find the rate and the thermal sensitivity of the material. So what we did is 2 cycles of loading and unloading to remove discontinuities inside the sample and let the sample reach critical state. Once the sample reached critical state, we started the velocity stepping to find the rate sensitivity of the material. Once we have this part of the test done, we let the sample reach critical state again, and we start increasing the temperature of the sample to find the thermal sensitivity of the material. So first, I will show you the results for the rate sensitivity. We have found that outside and inside the shear band, the results are exactly the same. We have a power law with the same value of rate sensitivity, which is 0.0135, sorry. And we can see that these results are very similar to the ones that Leyenhügel obtained in 1974, also for clay material. And the value of rate sensitivity is also very similar. Moving on with the thermal sensitivity, we found that we obtained the same exponential law, but with different values of thermal sensitivity from outside the shear band, which is the orange one, with a value of 0.0136, and that inside the shear band, the thermal sensitivity was higher, with a value of 0.04. So because we found that the rate sensitivity is exactly the same for outside and inside the shear band, but the thermal sensitivity is different, then we did micro scale tests to try to understand why we obtain these results. So we perform SEM EDS tests to see the fabric of the mineralogy of each sample. Then we also perform X-ray diffraction to see the mineralogy, micro-CT tests to see the porosity, and also plasticity index tests. So what we found, I highlighted here the center of the shear band in red. So what we found in terms of fabric is that outside the shear band, the minerals are randomly oriented, the phyllosilicates are face edge contacts, and they are very folded also because they are shades. But as we get close, right above and below the center of the shear band, the minerals are starting aligning, and the folds are smoother. And at the center of the shear band, all the minerals are completely oriented parallel to the shearing direction. So the mineralogy we found was between 20 and 30% of quartz, and then between 70 and 80% of phyllosilicates, that they include muscovite, chlorite, and paragonite. Then what we found is that the porosity and the plasticity index have the same behavior in depth, meaning that outside the shear band, they have average values, then right above and below the center of the shear band, the values are smaller, and at the center of the shear band, the values are higher. These two, right above and below the shear band, is because the reorientation of the mineralogy and also the pressure. And this is due to the completely alignment and contacts face-face, which are weaker than the face-edge contacts between phyllosilicates. And this is the displacement that I showed before from the inclinometer. So this is a sketch that I did to represent more or less roughly the evolution of the fabric from outside to the center, outside the shear band to the center of the shear band, which we call area of intense deformation, which is, as I said, completely aligned. The mineralogy is completely aligned parallel to the shearing direction. And I also need to say that the exact thickness of the shear band is unknown for this case study. So now that we obtain all the results, we can answer the question on why we had the same rate sensitivity from outside and inside the shear band. And it's because we have the same mineralogy in all the samples. However, with the thermal sensitivity, the difference of the values, we can see that the behavior is the same in depth, is due to the fabric, the orientation of the mineralogy. So it is very important to see very well the contact between the minerals. Because as I said earlier, if we have face-edge contact, it is a stronger contact that you need more to apply more pressure to create movement. However, if you are face-face contact, you need less pressure, and it's easier to accelerate the landslide. So now to test to validate and test if actually there's any change in temperature when a landslide is accelerating, we instrumented this lobe here in the S10, where you can see here better. We instrumented with UPC, with Polytechnic University of Catalonia in Barcelona, 3 piezometers, 2 above the shear band and 1 below the shear band. And we from the university added a thermometer at the center of the shear band. So the data shows that here is the water pressure from this piezometer, where we see that is empty. There's no water. However, below the shear band, there's a lot of water pressure, meaning that there's a pressurized aquifer below that is the one that drives the landslide and accelerates it. And this is probably because the shear band creates an impermeable layer that doesn't allow to to have a free aquifer. No? So here we also have the temperature data from the thermometer. And I also need to say that the piezometers also measure the temperature, where we see that it's mostly constant in time. However, in the thermometer inside the shear band has a lot of variations, which now I will show you that they follow very well the behavior of the pressure from the pressurized aquifer. So now that we have the field data and the experimental data, we apply everything to our mathematical model. Remember the heat diffusion equation in dimensionless form with the Grunfeld number and the temperature at the exponential. So the input data that we apply to the model is the field temperature and the water pressure from the piezometer below the shear band. And here we have our stress equation to calculate the shear stress. And then we also have the rate and thermal sensitivities from the experimental test that we perform in the customized thermal triaxial. And here we have the Grunfeld equation. This is a bit different because we have here the initial Grunfeld number equation, okay? Because for each case, you always have lags of different data. And for this field case, what we lack is the reference shear stress, even though we can have a range of values due to the depth of the shear band and the material that we have above the shear band. And then we also don't know exactly the thickness of the shear band, but we have a range of values because of the SEM test that we perform, which is less than half a meter. So because we don't know the initial Grunfeld number, we perform a Monte Carlo method for 500 simulations to calculate G0, comparing, calculating the temperature and comparing it to the field temperature, obtaining a very good fit with this value of G0, of initial Grunfeld. So now that we know more or less this thickness of the shear band, where we observe it from core logs and this microscale test that I show, we also know more or less a range of expected reference shear stress due to the depth. We calculated with an inversion of values for thickness and reference shear stress for different values of thermal sensitivity, okay? To try to understand which value first of all, if we need thermal sensitivity in our model, meaning that the temperature plays a role, and also because we obtain different thermal sensitivities, which thermal sensitivity would be best to get to obtain most fitted to the reality, no? So here we have the calculation of the model for without any thermal sensitivity, and we see that the range of values of the shear stress for the expected thickness of the shear band is completely out of scope from the depth that the shear band is. Then if we calculated for the thermal sensitivity, we obtain outside the shear band, and we see that for the expected thickness of the shear band, the reference shear stress is also high for a 30 meters depth. However, for if we take the thermal sensitivity of 0.04, which is the one that we obtain at the for the samples at the center of the shear band, we obtain a very good fit for the expected reference shear stress. Therefore, we can see that actually we need to take into consideration the thermal sensitivity and also which one, if outside or inside. And as we can see here, we need to test and obtain the thermal sensitivity from the material inside the shear band of the landslide. Now, with all the values obtained from the inversion of the model, from the field, from the experimental test, we have here the forecasted the field displacement in red, the cumulative field displacement from the extensometer that was installed, and we also calculated with all the values the forecasted displacement. And as we can see, we have a very good fit. And finally, the goal is to plot everything in our phase space to see where we at, if we are close to the tertiary creep, so outside this this gray area, or if we are in a safe space, meaning that we are far from the gray area, from the white area. So here, what we did is, this dashed line in purple is the pressure, the water pressure from the piezometer below the shear band. And here we have in the dashed line black, dashed line, the field temperature, where we see that the variations of either both the water pressure and the temperature follow very well. They have more or less the exact same behavior, meaning that the material is very responsive to pressures, to external loadings, and then we calculated the temperature in the model with all the values. So we calculated the temperature in the model with thermal sensitivity and without thermal sensitivity. And we see that we have the exact same values. But when we plot it into our phase space, room phase number normalized temperature, or is equal to external loading to shear band temperature, what we see is that the red one is with thermal sensitivity that follows the lower branch of our steady state curve, and that the blue one without thermal sensitivity is not following the steady state curve. And also, if we extrapolate the behavior, we see that it's unconditionally stable, meaning that if we don't take into account thermal sensitivity, the landslide would never collapse, which is impossible. Therefore, here we prove that actually the thermal sensitivity is necessary. And finally, what I wanted to show you is the Vardulakis forecasting model applied to different case studies that are mapped in the same phase space, normalized pressure and normalized shear band temperature. So there are 4 case studies plotted here. The first one, so we have 2 that already collapsed, which is the Bayonne landslide and the Mud Creek landslide that collapsed in 2017 in California. And then we have the 2 landslides that remain stable and they are still creeping, which is the Shuping landslide in the Three Gorges Dam in China, and the one from El Forn, which is the red one, which is still very stable. So this is what I wanted to show you, that first, the temperature we see that is imperative to have it and to control it, to have a better understanding of the mechanism inside the shear band and why the landslide behaves, how it behaves into the external loading, knowing very well the material that forms the shear band of that landslide. And also here you can use this phase space to map where your landslide is, if it is far from collapse or if it's close to collapse. So you are able to take remediation measures, meaning that maybe you can remove water, lower the reservoir level if the landslide is driven by variations level from the dam, etc. And thank you very much for your attention. I will be happy to answer any questions if you have.
Thank you so much. We are going to allow all the attendants to write their questions in some seconds. Maybe they appear here in my screen. Please, if you have any questions, you can write them right now. And here in Zoom, we have a question, Dr. Maximilian Alveoli. Go ahead.
Okay. I've been waiting because I have a kind of silly question, because I've been listening to your presentation. I didn't watch the slides, so this could be very off, but still.
Oh.
So yeah, I've been listening only. So from the last slides, I understand temperature is basically a key variable in your approach for understanding if the landslide collapses or not. So just to trigger the landslide. Before you said that, I was meaning to ask, is temperature in your model, in your description, more relevant for triggering the landslide or for its subsequent, I don't know, evolution, run out or something? As I said, I just listened to the presentation. Maybe this was a trivial question.
Yeah, no. Actually, it's a good question. Yeah. Do you have anything? No. Okay. So yeah, so it is sometimes complicated because you need to understand very well how the material of the shear band behaves. Some of them behave that once the landslide starts accelerating, the temperature increases due to the friction. But in this case, we have seen, because we have readings every 20 minutes, we have seen that first, there's an increase of water pressure. 24 hours later, there's an increase of the temperature inside the shear band, and 24 hours later, there's an acceleration of the landslide. So,
so is this temperature variation due to pressure variation?
In this case, for this material seems to be more like stress sensitive.
Okay, so it's not external temperature. That's what I'm saying.
No, it's
okay,
the temperature
good. I understand.
at the shear band. Yeah, exactly. This is what we take into account: the temperature at the material of the shear band.
Yeah,
because
as I said, I didn't see the equations. I just
no. It's a very good question, because maybe sometimes, because I have it, I know very well. Sometimes it's like you don't express it well, no. But yeah, because also we are talking about deep-seated landslides where the shear band is in below 10-meter depth. So the external temperature from the environmental temperature, in this case, it doesn't affect.
Thank you very much.
Thank you.
All right, let me read this question from YouTube. I even pasted here. It says, during tertiary eclipse, there was no rain event?
Can you repeat the question, please?
I'm sorry, during tertiary eclipse, there was no rain event? I pasted
during tertiary creep, it there can be a rainfall event. For example, for the case of the Mud Creek in California that collapsed, this landslide collapsed after days and days of very, very big rainfalls. So meaning that the sliding mass is very saturated in water. The capacity, so the water level of inside the sliding mass is so high for the resistance of the shear band material, where the shear band is very, very thin, that it cannot support that high amount of groundwater and then collapse. But yes, a lot of them can be due to rainfall, for example, large, because we are talking about deep-seated landslides, which involve millions of cubic meters of rock mass. They have to be like very big rainfalls and continue during maybe weeks sometimes, but it can be random also, no?
All right, thank you so much. Also for the questions. Then I suppose it is the end of this presentation. We don't see any more questions. And also,
I will stop sharing. So thank you very much for having me. It's been a pleasure, and hope to see you soon again in another conference.
Yeah, absolutely.
Thank you very much. Bye bye.
Thank you. Yeah, it was an honor for us to hear this presentation, Carolina Segui. Now, if you are following me or following as I am doing right now the conference schedule, we had a time for a discussion section. Unfortunately, we just have right now like 20 minutes. So we can take those 20 minutes as a break, but also we have the links on the conference website. These are links for Meet. So on the conference website, we have those links, and we can use it if you want to talk with others. I am going to be there any comments you want, or just we can come back in those 20 minutes. So see you there or see you soon. Please. All right. We are having some seconds waiting for all of you to come back to the streaming. We are very happy to share with you, to also be with those magnificent speakers that have been with us during those 3 days. And in the Landslide Scientific Assessment Conference, we had the opportunity to listen and to watch the presentation of Rosario Vasquez. The title of the paper that they published is Numerical Modeling and Hazard Implications of Landslides at the Ardillas Volcanic Dome, Tacana Volcanics Complex, Mexico, Guatemala. Let me say hello to Rosario. How are you?
Hi, Roberto. Thank you.
That's great. Thank you so much for accepting the invitation to present in this event. We want to know about your affiliation, but maybe anything you can describe us about your research, about yourself, and then you can start with your presentation. Thank you.
Well, thank you first for inviting me to this conference. And well, I'm from Mexico. Excuse me. Excuse me, but I hear my voice twice. I don't know why. And actually, I was hearing you also twice. Can we check why?
Right? We are sorry. We are sorry for those technical issues. Now it is okay. Please, Rosario, continue with your presentation, and thank you so much.
Well, thank you again, Roberto, for your invitation. And well, I'm from Mexico, and currently I'm working as an associate professor here at UNAM, which is the National University of Mexico. And the research that I'm going to present you today was funded by the National Council here in Mexico of Science and Technology. And this is just one of several hazard maps that we have been preparing for the Tacana Volcanic Complex. And I'm going to talk to you today about the map that we integrated for small volume landslides. And this is a work with many collaborators, and I'm representing those other colleagues. And just to begin, let me share with you the name and where you can find my paper, which is published in Natural Hazards Journal. Here is the DOI. And I think I'm going to use this one. Okay, better. Just to let you know where you can find one of our works. So let's begin by sharing with you where is located the Tacana Volcanic Complex. I've seen in yesterday that many of you have talked from several types of landslides and several contexts. And well, I'm going to present you a volcanic context. Yes, we made some numerical simulations about an active volcano that you can see here. It's a part of a volcanic chain named the Central America Volcanic Arc, or also known as just Cava, and is the northwesternmost volcano located in this volcanic chain that extends from more than 1,000 kilometers down to South America, actually down to Panama. It begins here in the borderline between Mexico and Guatemala and extends southeast down to Panama. And this volcanic complex is located in a very complex tectonic situation also, because we can see in this part of the map that there's the Middle America Trench that is a tectonic setting characterized by the subduction between mostly the Cocos and the Caribbean plates. But we also have in here another important tectonic setting, which is set between the movement between the North American plate and the Caribbean plate. And this movement resulting in this Polochic-Motagua fault zone that, as can be seen here, is it's a lateral left strike slip fault zone that promotes also not only the volcanic activity in this region, but also there is a lot of seismicity within this zone, not only provoked by this situation, by this subduction zone, but also because of the Polochic-Motagua fault zone. And this is where we can find the Tacana Volcanic Complex. So these two are important features that could lead eventually not only to a future volcanic eruption in the near future, but also to the formation of landslides. And let's talk about the geology of the Tacana Complex. We can see here in this plan view map the general geology of the complex, which is colored in brownish and reddish and yellowish colors. And we can see the complex that is surrounded by other volcanic features as the calderas named Chanjale, San Rafael, and Sirinal. These features actually function as natural barriers for the volcano, which was constructed inside the San Rafael caldera. Now, if we see this profile from northeast to southwest, and from the oldest to the youngest structure, we have the Chichu volcano, the Tacana volcano, Ardillas Dome, and San Antonio volcano. And actually, San Antonio volcano is the youngest structure of the main complex, but well, it's from the Holocene. But we can see that the Ardillas Dome, that is this little thing right here, and this little bump in this topography, Actually, we're not very sure about the exact age of the Artillas dome, because we are supposing that it must be older than 760 years before present, because at this time we found some surge deposits around the summit of the volcano that were produced from an explosive eruption of this age that left deposits all over the summit. And one of our colleagues that also was working with us to obtain this research, he obtained chlorine 36H for the Artillas dome, but he described that this age that was dated in 300 years old, that is a lot more younger than the other structure. He described that that's probably not the emplacement age for the dome. So we are supposing that this structure must be older because it was intruded between the Tacana and San Antonio edifices, and it's also covered by the deposits of this explosive eruption. So we can see a zoom in to the summit of the volcano, where we can see the units of the geology of the main structures of this volcanic complex. The Tacana volcano, as can be seen here, is formed by two, and one of these domes is dissected in two, so it forms like three little domes. The Artillas dome that is intruded between these two structures. And we also hear this little polygon colored in blue that we think that it was probably originated by the explosion that left the eruption of 760 years before present. So it is also at one side of the Artillas dome. Now, I present you in this scheme a summary of the main volcanic processes that have taken place within the Tacana volcanic complex. We have found in the surroundings of the edifice at least 11 pyroclastic density currents, or at least 11 deposits associated with different types of pyroclastic density current, mostly block and ash flows, which are signaled as BAFT. We have also mapped at least 6 Plinian to subplinian type eruptions that have left very sparse deposits of asphalt deposits, I mean. And we have also found several stages of effusive activity characterized by 25 lava flows. What we have encountered also are 5 big deposits of debris avalanches, and at least 2 events that have developed syneruptive lahars during the entire history of the Tacana volcanic complex. We can see from this scheme that most of this activity has concentrated at the Tacana edifice. Okay, but the main thing about this research is the Artillas dome. And we can see from this map the structural features, I mean the fractures and the fissures and the faults that are currently dissecting the volcanic edifice. And we can see that the main orientation of these features are consistent with the same orientation as the volcanic complex main edifices, which is northeast, southwest. And let's focus within this area, which is marking this collapsed scar from the Artillas zone. We can see from this photograph that was taken from southwest towards the summit of the complex, and we can see within these yellow lines the top of the Artillas dome, which is located in here. And these are some features that are marking this zone that is breaking up. I mean, it's half fault and half fractures that are dissecting the Artillas zone. And this is the main direction, which is towards the southeast. And it's opening the surface of the main part of the dome, and it's going towards this direction. We can also hear, we can see here also from this photograph the little crater lake that was formed due to the 760 years explosive eruption. And we can also point it out within this photograph the site of one of the most recent eruptions that has been taking place within the complex. I mean, we have two phreatic explosions atop of the Tacaná volcano. The first one in 1949 and the other one in 1986 that was situated down here, right in the scarp of a previous collapse of the main edifice. So all these features are, as we can see here, aligned or are mainly controlled by the structural features that we can see from this aerial view of the volcano. Now, this is the main objective of the research that I'm presenting you today, because during the field campaigns, we detected within this area a surface that could be prone to be detached from the main Artillas zone and potentially could form a landslide. So we detected this from our field campaigns. From this other view, we can see the shape of this surface that we calculate the maximum volume that could be detached from this zone. This is the shape and the size of this surface. And we detected also that you can see here, this is the beginning of a very narrow and deep ravine that is called Maxam Ravine. And this is a photograph from an active debris and rockfall zone that we detected just atop of here, atop of the Maxam Ravine. And all these conditions give us the reasons why we started to do this research, because we detected that right now there is an active zone that is having rockfalls and have all these debris from the vegetation. And this site is characterized not only from these structural features, but also we have superficial hydrothermal alteration that is taking place all around the summit of the volcano. So we have a lot of debris that could still accumulate within this part or even downflow the Maxam Ravine. So what we did was to perform a series of numerical simulations of this zone that could be detached from the southeastern side of the Ardilla zone. And we estimate using the 3D analysis tools from ArcMap of Esri, a maximum volume of 25 million cubic meters of material that could be detached and to form a landslide. And for the landslide modeling, we decide to use the Titan 2D model, which was developed by the research group of Pittman and Patra and colleagues at the University of Buffalo. And this is a depth average model based on frictional Moore-Coulomb behavior for shallow water granular flows in order to simulate the formation of future landslides sourced within this zone. So first, what we did was to perform a sensitivity analysis in which we used digital elevation model as input of 5-meter pixel resolution. We distributed these 5 source points along the main fractures and fissures that we detected that could be the starting point of a landslide within this zone. And we also varied the amount of material, I mean the volumes from possible landslides. And I want to explain that the maximum volume simulated was this value that we obtained with the ArcMap tools of 25 million cubic meters, but we also decided to simulate volumes with a lesser volume. We ranged these volumes from 100,000 cubic meters up to 25 million cubic meters. And for the other input parameters, we decide to maintain the internal friction angle and the basal friction angle, as well as these input parameters within all the simulations the same, because these values were obtained from the calibration of this model in a previous work made by me and my colleagues for block and ash flows and debris avalanches, also simulated around the Tacaná volcanic complex. So with these values and the variation of these input parameters, we start to modeling future landslides originated within this zone. So let me show you some of our results. First, in these maps, we can see the outcomes from the first series of simulation, where we decide to use the same input volume, which was 100,000 cubic meters, and we vary, as we can see here, the input source. These input sources, these point sources that are distributed within this zone, we vary the point where the landslide was about to begin during the simulation. And we noticed from this first set of simulations that if we maintain the same volume in all those cases, but instead we move the source origin for the landslide, the outcomes did not vary much. I mean, we can observe from this set of simulations that the outcomes are similar. I mean, the maximum distance reached by the landslide was about 4 kilometers, covering an area of 1 square kilometer and reaching a depth depth within the Maxam ravine of 6 plus minus 0.2 meters in all the cases. So the source point was not so sensitive as we can see from this result. But second, on a second part, on a second set of simulations, we obtained these maps where we can observe that letting the same source point, but varying the input volume from the smallest volume that was 100,000 cubic meters up to 25 million cubic meters, we can observe that the results vary a lot. I mean, if we increase the amount of volume involved within the landslide, the surface impacted or affected downflow by the landslide was bigger, obviously. But if we only observe the three first maps, one of the main outcomes that we can observe is that there's still the biggest part of the landslide is delimited to the topography of the Maxam ravine. But when we reach the simulation where we involve an input volume bigger than 2.5 million cubic meters, part of the material associated with the landslide begin to expand or to distribute to some other parts outside of the ravine. We also can observe that the maximum length, the maximum depth, and the surface covered by this simulated landslide will vary according to the simulated volume. So this is the main input parameter that affects the outputs of the model, as we observed this behavior before while using the Titan 2D model. And with these results, we also perform an analysis of the potential damage that the biggest landslide that we simulate could do to the localities settled in the southern flank of the volcano, which is the most impacted with considering this scenario. We consider this scenario the source point B, which is the tallest, with the biggest volume simulated as the worst case scenario from all the simulations that we run. And this analysis, we perform it based on the intensity index for debris flows that was proposed by Jacob and colleagues in 2012, and is based on the expected depth and the maximum flow velocity for the in that case for debris flow, but in this case for landslides. And within this index, we can estimate the sort of impact force of the landslide. And those authors propose probability matrix, well, damage class probability matrix, where they classified according to the level of destruction or the impact done to the buildings, the level of losses that those buildings could have. So we use this model using the values that we obtain from our simulation, from this worst case simulation, where we can see that impacted at least 8 villages. They're in pale blue. And we obtained a map for the intensity index that we represented on a color scale from yellow to red. And according just to this map, at least 5 villages will suffer some sedimentation, which is colored within the yellow zone. 2 villages will endure some structural damage that are distributed within the orange zone, and 1 village will have major structural damages that are inside the red zone. But while we were doing this analysis and we compare the probability matrix that we obtained with the depth and velocity values according to the distribution map to the distribution of the intensity index within this map, we observe mostly that there are some inconsistencies between the values obtained from the metrics and what we can observe from the distribution of the deposit left by the landslide. And we are thinking that probably these inconsistencies are due to some uncertainties associated with the estimation of the exact velocity of impact of the flow. I mean, we can obtain a very certain velocity value mostly inside of the ravine where the model is calibrated. But in these areas where the fine particles of the landslide could surpass a high topography, in those places, like in here, the level of certainty about the calculation of the velocity of impact is not that well estimated by the model. So we have some level of uncertainty in some of these zones that we think that probably it's because of that the values that we obtain from this probability matrix compared to the map do not match that well. But it's an approach that we're still working on to enhance our results and the maps that we obtain. But the main objective of this kind of maps is that we can see the distribution of the deposit that we can left a very big landslide where it will affect at least 8 villages, and within these villages lives more than 2,000 persons. And within these villages, there are also constructed at least 370 dwellings that could be impacted in some extent by a landslide like the one we're showing here. So some aspects to discuss. Well, as I already mentioned it, the volume of the surface prone to be detached in the southeastern side of the Ardilla Dome could have been overestimated due to the methodology that we use for its calculation. The tools that are set within the 3D analyst module of ArcMap uses the volumetric difference between two surface models. So this surface could be could have been not placed in the right place to estimate the volume at top of this surface. So we are aware that probably we overestimated this volume. So this is why actually we decided to simulate landslides of minor volumes with a minor volume of material involved. And from the sensitivity analysis performed to the model, we also observe, as we show you in the maps, that the input volume is the input parameter that has the biggest effect on the behavior of the simulated flow that we obtain, especially in the impact in the longitude or the size of the impacted area and the maximum distance reached by the flows. We also observe this fact that in those landslides involving volumes bigger than 2.5 million cubic meters, just those landslides bigger than this value will surpass the narrow topography of the Maxam ravine, and actually it will also surpass a ridge that is located south of the Chichuk volcano, which is a relief or a characteristic of the morphology of the volcano that naturally should serve as a barrier for those villages settled in the back of this ridge. But due to the location of the source of the surface that could be prone to be detached, that is very steep, even landslides involving more than 2.5 million cubic meters material could surpass this ridge and affect the villages that are settled in this backside of this ridge. And actually, within this ridge is located a village named Chiquihuite. This is important, and in a few slides, I'm gonna show you why. And finally, the last aspect to discuss is that the intensity index analysis that I just showed you in the last map, we detect these inconsistencies between the index reflected in the map and the classification obtained from the probability matrix. And as I just explained to you, this could be due to the uncertainties associated with the estimation of especially the velocity. It could be also due to the estimation of the expected flow depth, but mostly because of the maximum flow velocity estimated by the model, but in those sites where are located the villages that could be impacted by the landslide. And as a conclusion, our conclusions are very important because we now have a better understanding about how landslides or different sizes, from small to a bigger size, would distribute downflow. I mean, in the down flanks of the volcano, where lives at least 2,000 people. And from our maps, we observe that there will be some sites or some areas that a landslide could reach flow depths bigger than 6 meters and have impacting velocity of more than 5.7 meters per second. And we also observe from this distribution of the deposits that the villages that could be impacted
Due to the materials of the dwellings that were constructed within these villages, we are certain that the potential damage to those structures will be important, because according to our map, we estimate that at least one locality will have some sedimentation, and according to according to the metrics that I just showed you here, we have discrepancies, but in this case, the probability matrix give us as a result that at least 2 of the villages impacted by the biggest landslide will be completely destroyed. And probably we cannot see these villages completely destroyed within our map, but we are certain that a landslide coming from the source in the Artillas Dome southeastern side will affect the villages located downflow. And the situation that is currently present within these villages, within these communities, is that the materials of the buildings that they have constructed, or the houses that they have constructed, will not resist a landslide, no matter how the amount of volume involved in the landslide. And we must also consider that the Tacanagua volcanic complex setting is characterized by one of the heaviest is located in one of the regions that almost all the year have heavy rainfalls. And this has developed a high superficial hydrothermal alteration. And as we can observe from the photographies that I just show you, the morphology at top of the volcano is very steep and is currently being dissected by these structural features as faults and fissures and fractures. And as I described at the beginning of my talk, it is a region of active seismicity because of the tectonic setting around the volcano. So probably not just the Artillas Dome, but all the complex itself has a high potential to develop landslides of different volumes that, considering the number of inhabitants that are currently living in the flanks of the volcano, we are aware that this area could in the future help with disasters, and disasters like the one that just happened last year. I don't know if you can see this video, but if not, you can see here a very small landslide. It was a video, sorry, but this was a very small landslide that took place during the rainy season of the last year, during September. And this community is the village named Chiquihuite. So due to the extreme rainfalls that were associated to a hurricane, part of the mountain developed a small landslide that at least devastated 3 small houses that were in the limits of the main community of Chiquihuite. Oh, now you can see. So we heard from this disaster last year, months after our research paper was published. So we're not that wrong studying this type of phenomena at Takana volcano. And lastly, I show you within this map the other potential detachment surfaces that we have detected around the summit of the volcano and in the lower parts of the edifices. And just to tell you, the Chiquibite community is settled right here, and the landslide that destroyed those little houses begin from here in a very low slope of the volcano. So we're considering that the main sources of landslides involving bigger volumes could be detached from the upper part of the volcano because of all of these conditions. And well, that's it. Thank you for your attention.
Thank you. Thank you so much, Dr. Rosario. It was amazing, magnificent. Let me check if we have questions here in YouTube. We invite all the attendants. If you have questions, you can write them in the chat. I am going to ask you one question. How do you think the model Titan 2D, the model you used, or the methodology in general, can help the landslide hazard assessment in terms of, I am thinking, for example, the part of the incorporating the volume or the intensity of a landslide is a challenge, is difficult for landslide hazard assessment. Do you think it can be a good approach, or is it still a problem that maybe this method requires that info as input data? Maybe in Titan 2D, we need to introduce as input the ADM, but most important, intensity or info of the possible mobilized material. What do you think about it?
Well, the input parameters do not consider the impact of the landslide. I mean, we calculate this apart from the model that we use, and probably there are a lot of other numerical models that could be better to address the hazard assessment posed by landslide in this zone. But there are problems within this area that they leave us no other choice. I mean, we are aware that we need more info to enhance our results, and probably we could use a better model to simulate these type of processes. But unfortunately, we don't have that much information. I mean, I think we mostly need a better topography of these ravines and more information about the futures of the materials within this zone, because we are considering that the landslide will be made from solid rock that could be detached from the southeastern side of the Artillas Dome. But we are seeing right now that part of the wall that is attached to the dome, it's been suffering hydrothermal alteration, not just because of the rain, but also because of the hydrothermal circulation of fluids within the volcano. I mean, we have very different conditions within this volcanic system that are very different from probably a mountainous setting, that probably the material is not hydrothermal altered. I don't know. And these parameters or these characteristics of the material that could lead to a different transportation or to a different behavior of the material downflow is important. But the model that we use right now, that is Titan 2D, does not consider this because it's not developed precisely to model landslides. I mean, it was developed to model other volcanic processes or of a bigger magnitude, like a debris avalanche or a pyroclastic density current. But that's the information that we use is the information that we currently have. And there are some areas, especially at the Ardilla Dome, that we cannot reach some of the areas of the surface where we can collect the material and experiment with it. But we cannot reach some sites because it's very steep, and the ground, or at least the materials that are in the surface, could lead to a fall down of one of our members. So it's not an easy zone to do field campaigns or to collect the samples that we need to characterize the materials in that place. So yes, it's very challenging.
All right, thank you so much. We are going to continue with the next presentation, and thank you for accepting this invitation again, and see you, I hope, another time. Blessings.
Yes, thank you.
All right, we are going to continue with the next presentation immediately. So let's have some seconds. We are going to prepare the streaming and everything. So we'll be back just in some seconds. All right. All right. Hello, everybody again. We are continuing with our day 2 of the Landslide Scientific Assessment. We are now the honor of listening Dr. Tiago D. Martins in the presentation entitled Mass Movement in Brazil, a Recurring Issue. I want to remember that he is co-author with Bianca Siviera. She was invited, they were invited to participate in this event. So let me say hello to Tiago Martins. Hello, doctor, how are you?
Hello, Roberto. I'm fine. What about you?
I'm great, and thank you. Thank you for accepting the invitation of being here. Please tell us about yourself, your affiliation, and you can start your presentation.
Okay, Roberto, thank you. First of all, I want to thank you and for inviting us to present some of our research here in Brazil. My name is Tiago. I teach at Federal University of São Paulo, in the city of São Paulo, and I am presenting I'm presenting these slides as well the paper that have as the leading author Professor Bianca Vieira from the University of São Paulo. Yes, we have a couple universities at the same city. I teach geomorphology at undergrad course in geography, the Department of Geography. And my main research focus is about landslide susceptibility mapping using some of the tools that I will present here. And this theme caught my attention because Brazil, as the title says, have a recurring problem regarding mass movements all over the country, especially in one of the landforms known here as Serra do Mar, that I will show some pictures. And this issue has bring to everybody a lot of attention because of the damage that caused every year. So first, I will present to you guys some pictures of this recurring issue in Brazil, and after we'll present a brief about the paper published a few years ago that has Bianca as first author. So landslides in Brazil are happens every year. They cause a lot of loss of life, homeless, and economic losses, of course. And we have some registers, historical registers since the 20s. But since the 60s, the studies regarding these themes are enlarging. It's getting more people attention, especially because the most susceptible, most prone areas to this kind of process are inhabited for a long time. It's the inhabitations in these areas are associated with the colonization process that started in the east shore and the east coast and to the hinterland of Brazil. So you can see this black and white picture from the 60s in the city of Rio de Janeiro. As you can see in the back of the buildings, a landslide that reached the urban area. Second, also in the 60s, we have some main moments in Brazil that the disasters caused by mass movements were very intense. On the 60s, 80s, and the 2009, 2010. So Serra das Araras is part of this landform compartment that faces the Atlantic Ocean, so this mountainous terrain that goes from south to the southeast Brazilian coast. So Serra das Araras is part of it. It's in the way from São Paulo to Rio de Janeiro. Next, you can see Santa Catarina. It's a southern state where the Serra do Mar, let's say, begin in the south, and especially in the Itajaí Valley. 2008 was affected severely by mass movements and debris and mud flows, and as well of floods. And then at least 140 people died. And Cubatão, that's a town, a city near São Paulo that holds one of the largest industrial plant we have, that was affected severely in 1985, as you can see the pictures. And this chart shows the number of people that were killed in these major events since the 80s until 2010. And unfortunately, we been registered in the last decade or so a number of events that cause loss of lives. And in this year, our rainy season here is our summer goes from December to February, March. So this is the rainy season. And then this chart shows this variation number of people killed. And unfortunately, as I said before, there are a lot of registered in the last decade or so, like in Petrópolis, and Petrópolis, the town of Petrópolis in Rio de Janeiro, and the town of Franco da Rocha near São Paulo, that register severe damage by mass movements and floods in this year, 2022. So, as I said before, summer is our hard moment. The rain season is starting middle spring, like let's say now, late September, early October, and keep increasing until summer that starts in December. And December, January, and February are the worst months for these issues in Brazil, that we have a lot of registers of this kind of process being triggered so by the rainfall and reaching urban areas. So as I said, often during summer, Brazil is affected for widespread mass movements, events, especially shallow landslides and debris flows. Those are the main types of mass movements we have in Brazil, and the triggering factor that stands out is the rainfall, especially during summer season. This is the city of Rio de Janeiro is in the coast, but the mountainous terrain that they call Serra do Mar is in the back of the Guanabara Bay. So this is the picture after this mountainous terrain has been affected by a large number of mass movements, special shallow landslides and debris flows in 2011. And two questions comes out from observing this. One is associated to evolution of landscapes. So these landscapes evolves through mass movements. And then in the other hand, in this landscape, we have the many areas under hazard conditions because it's well populated. It's the first area that has been widespread populated since colonization times. So, as I said before, economical, social, environmental laws are very common when these mass movements are triggered. And a recent study in Brazil showed that at least or more than 8 million people living in risk areas in Brazil associated with mass movements and floods, especially shallow landslides and debris flows. And these slopes that form these landforms carry a larger volume of sediments and reach a large volume of sediments are carried to the drainage network, filling up this drainage network and building up this kind of landscape that presents steep slopes with a lot of material prone to be moved, and bottom valleys that are prone to floods or to carry debris. And of course, these bottom valleys are in some place occupied by urban areas or by farmers. So the combination of this land use associated with the mass movements, but 8 million people in Brazil living under risk conditions. Serra do Mar is this landform compartment. It's this mountainous compartment that face the Atlantic Ocean, as you can see here in this map. So you can one of the key characteristics of this area are steep slopes, and some of these areas get a lot of rain during all year, especially during rain season. So as I said before, the idea that this kind of landscape evolved through mass movements give us a better understanding about the genesis and the evolution, and especially the recurrence of the process. So Serra do Mar, this landform compartment, as I said before, it's very peculiar. Used to be forest all over. Of course, due to the colonization process, the forest has been diminished severely. And also rainfalls have reached high values in this compartment. So we call this landform Serra do Mar, that is because it's faced to the Atlantic Ocean. So it's a kind of a step from the Atlantic shore, lowlands of the Atlantic shore, that separates this Atlantic shore lowlands to the hinterland that's a more plateau terrain. And we have a lot of register of mass movements that are somehow covered by this vegetation. And as you can see here in the picture, steep slopes covered with rainforest are the two main characteristics of this mountainous range that extends about 15,000 kilometers since the north Santa Catarina state, north part of Santa Catarina state, until the southern part of Rio de Janeiro state. And you have a sort of parallel mountain range that goes a little bit, goes north. We call all this system the Mantiqueira system. But our research focus is in the Serra do Mar mountain range. Another important thing about this landform compartment that holds big cities, holds pathways that are that have a very important, very economical importance. This region has a significant economical importance since it is crossed by railways and highways that connects the Brazilian large cities, São Paulo and Rio de Janeiro. And these highways and railways are very useful to export our commodities, our goods that are produced in the hinterland to the ports, especially the Port of Santos. Port of Santos is located in the shore, of course, and the São Paulo city is just in the back of this mountainous range here. And you can see also very important highways that cross the area, as well railways that go meandering, if I can say so, around this mountainous terrain and reach the main cities in the counter hinterland. So one of the main events that happened in Brazil, it's in the 60s, 66, 67, that were well studied. This is the city of Caraguatatuba in the shore of São Paulo state. It has been severely affected by mass movements and debris, mass movements, shallow landslides and debris flows. You guys can see here the landslide scars produced by this process, and here you can see the highway. So this process happened in the March 16, 17, in 67, were first studied by deployee in Cruz that mapped the deposits and the outreach of the deposits associated with the mass movements. In fact, if you go to the Caraguatatuba today, nowadays, and you stop at the same point of this picture, that is a sort of viewpoint in the road, you can see the landslide scar preserved by some sort of peculiar vegetation that grows in the area, that in stopping the forest to recovering. Another picture here regarding the mass movements that affect Serra do Mar mountainous terrain. And this is near the city of Cubatão. You can see here the slopes that form Serra do Mar. And exactly in this area that contains the watershed that will present you guys a little bit ahead. And this area is very important because you hold here highways that are used to transport the goods produced in the hinterland to the port of Santos. And as well, you have here some industrial plants that are very important for Brazil. And these plants are situated in the footsteps of these slopes that are very prone to mass movements. Another event that happened was in Rio de Janeiro with more than 55 people killed in 1996 in the city of Rio de Janeiro. That were two watersheds affected by mass movements. As you can see here, debris flows with very large blocks being moved along the drainage system. And this happens one of the massifs that you can find inside the Rio de Janeiro town. Is a bit far from the Serra do Mar mountainous terrain. And here you can see the Itajaí Valley located in Santa Catarina state. Is the southern part of Serra do Mar mountainous terrain. With a similar physiography, you can see steep slopes surrounding the bottom valleys that are used for farming. And these bottom valleys are filled with sediments. This event happened in 2008 and killed you guys may have seen during the presentation the amount of rain that was recorded. This is one issue about our research here. Usually the rain gauge is not at this point, so we somehow make some estimation to understand how much rain happens during the event. But like this one, it's 720 millimeters in 72 hours of rain. It's quite a lot of rain, and causing these mass movements. And here in 2011, the Serra do Mar in the state of Rio de Janeiro was severely affected in the 11th and 12th of January, 300 millimeters in 48 hours, causing widespread mass movements in these towns located in Rio de Janeiro state. It's not the Rio de Janeiro city, it's in the Rio de Janeiro state. This is a bit west of Rio de Janeiro city. And what all this occurrence, all these events that I'm been reporting you guys, made the Brazilian government create a policy that in order to prevent risk situations like those I just showed you guys. And we have a law since 2012, a year after, that require the municipalities to make susceptibility maps for the towns that are located in this kind of terrain. And we have a national center that was created in order to monitoring rainfall and risk areas for Brazil. So all these occurrences encourage the government, encourage not the best word, but force the government to take actions. And this law was passed in 2012, and this national center was created as well. So another example here happened also. 2010, 2011 was a year of disaster in Brazil. We have a lot of registers regarding this kind of process. Here you can see a pic of Google Earth, seeing the shore and the mountainous, this Serra do Mar mountain range, this step that separates the lowlands of the shore and the hinterland. And one of the affected cities is this one, São Luís do Paraitinga. Was affected, the town itself was affected most by floods, but the area around the town was affected by shallow landslides. So more than 500 landslides were recorded during the late December 2009 and early January 2010. And during this time, we registered at least 600 millimeters of rain. And there's some pics of the São Luís do Paraitinga because this is a historical city in Brazil. And also there is a cultural value for the city because in the 17th and 18th century, there was a pathway from the Minas Gerais, like the area that produced gold, the mining area in Brazil. There was this pathway that connected this mining area to the shore in order to export gold and diamond. So this path became a sort of tourist attraction, and many people used to go through this path as I said, tourist attraction. And São Luís do Paraitinga is a part of it. So besides all this damage, there is this cultural meaning about the cities that grew along this pathway, and all this historical value and the national and cultural heritage that was built on this path. São Luís do Paraitinga is one of the cities, as you can see pictures here from the 50s. And also São Luís do Paraitinga attract a lot of people because of these folklorical parties. And the main plaza of this folk meetings is in front of the main church. And this main church was destroyed during the floods of 2009, 2010. The Paraitinga River flooded and occupied all the historical center that goes from this another church here, this street and here, and destroyed the church. This church was, it was at least 200 years old, was built not with concrete, was built with more ancient techniques, and could not handle the amount of water and collapsed. As well, you can see here the river banks collapsed. So today the church was rebuilt, and all the river bank was reinforced, the structure. But here you can, one of the clear example about our risk areas in Brazil. People living near the riverbank or occupying steep slopes prone to mass movements, and all this heritage that also occupy areas that are suitable for mass movements and floods. Here you can see what's left from the church that collapsed in 2000. It was early 2010. And another part here that was the municipal market, but the municipal market did not collapse, but all the town was underwater. And another main event that happens here in Brazil was in 2014. In the southern part of Serra do Mar, we have this, we call it Ribeira Valley. It's the valley formed by the Ribeira do Iguape River. That's one of the most preserved rainforest areas in Brazil, in southern Brazil. And in 2014, January 2014, intense rainstorms, nearly over 120 millimeters in 72 hours, triggered hundreds of landslides and debris flows that also reached the town of, especially the town named Itaoca, and destroying the town. So the mass movements happens in the upper valley, but the debris reach the bottom valley, and the water carry the blocks itself, as well the wood, the trees, and this more fine sediment and the trees that reach the town and destroy their infrastructure, as you can see here. This bridge that is in the central part of the city hold all this wood material, and the river start to overflow its banks and reach the town, and also during the process the wood that were carried along the river start destroying the house. 25 people were killed, and at least 300 people were homeless during this episode. So, saying that, this background about mass movements in Brazil, I'm presenting here some brief aspects about the paper entitled Assessing Shallow Landslides Hazards Using the Triggers and Shell-Stab Models in Serra do Mar, Brazil. This paper was signed for different authors, and the leading author, as I said in the beginning of the presentation, is Professor Bianca Vieira from the University of São Paulo. So the idea about this paper was to compare the performance of two different models, two physically based models, triggers and Shell-Stab. Shell-Stab is a model that has been applied in Brazil since the 90s. It's a well-known model here. Different assessments, and triggers is a less used model. So the idea of this paper is to compare the efficiency, and as one of the questions is which method is best. Like, there are a lot of methods in order to map susceptible areas to some sort of process, in our case, mass movement. So some methods are based on some level of understanding of the process, and you can infer a weight on some parameters. But these methods rely a lot on the experience of the researcher. So physically based mathematical models use not to rely on the subjective experience of the researcher, and instead applies equations that describe physically relevant process disregarding subjective opinions. So the idea was to use models that we know that are low cost, that the inputs are based on some physical parameters, and the results are based in some equations, and these somehow avoid some subjective or opinions. So these models also can be used to predict landslide susceptibility under different land use scenarios. The study area evaluated in this paper is one of the watersheds that reached the city of Cubatão, one of the pictures I showed before. So encompass 3.6 square kilometers, and in the bottom of the valley, or in this watershed, we have a large petrochemical plant built in the 59, and a large industrial park. All this located in the city of Cubatão. So Cubatão is a city that are in the Serra do Mar, and behind the Serra do Mar to west, you have São Paulo city. To the east, on the shore, you have the port of Santos. Some characteristics of the watershed. 60% of the hill slopes are between 400 to 800 meters elevation. So this is something curious. Serra do Mar varies the elevation depending on where you are. So you have in São Paulo specifically, the altitude is not as high as in Rio de Janeiro or in Paraná. So Serra do Mar reached higher altitude in other points. And 42% of this the slopes are within 30 to 40 degrees angles. So it's a quite inclined terrain. And as you can see by the numbers, are located a little bit far from the shore. So the idea was to test different scenarios using these two models. And for all these models, the main data, the main input are the digital elevation model, the digital elevation data. So one of the issues where we are working on here that are that we can choose two things when we decide to use these models, the DEM and the landslide scars, because the model, the equations behind the model are already there. So you can vary the parameters, but the equations will allow the computer to create these scenarios, and the equation does not carry any variation. So besides the DM and the landslide scars, we can test different values of inputs, and as you can see here. So 6 scenarios were tested for each model. And the main issue is the variation of soil thickness and the cohesion. So the first 3 scenarios, cohesion was used 1,000 pascals, and in another scenario 6,000. So this, and also you can see a total unit weight of soil varying a little bit, and also the soil maximum thickness from 1 to 3 meters depth. And the other values are quite the same. So the idea is which model responds best, varying this parameter, if you compare the number of cells to the landslide scars. So for that, there is 356 scars were mapped from the 1985 event, what represents 3.7% of the total area of the basin, and two methods were used to compare. We call it scar concentration and landslide potential. The idea is when you compute, it doesn't matter which model is it, you present different cells. Each cell has a value. The idea is to see what cell is in the land scar perimeter and check if the landslide scar is coincident with the cell that says is unstable or stable. So the scar concentrations presents the ratio of the number of cells in each susceptibility class affected by shallow landslides to the total number of cells in the basin, and the landslide potential somehow gives us a different perspective because shows if there are a lot of cells that are unstable in the total area of the basin. In simple words, if you paint all the watershed in red and say that's unstable, we can assume easily that inside the landslide scar will be red as well. So the idea is somehow balance this evaluation from the scar concentrations to the landslide potential, being the less the ratio of the numbers of cells in each susceptibility class affected by the shallow landslides to the total number of the cells in the same susceptibility class. So using this model, the idea is not to say all the watershed is unstable. So it would be an easy answer. Somehow the scenarios must balance stable and unstable areas. As I said before, there were a lot of landslide scars in the 1985 event. These are some pictures of the area. As you can see, the shallow landslides happens in the upper slopes, and the material reaches the drainage system, and all this flows as a debris flow to the lowlands of in the foot slopes. So one important thing to say is that shell stub or triggers are models used for shallow landslides, not other process. So the idea here was to verify which model fits, which scenario fits best the landslide scars, and this is another issue we've been addressing here. Which landslide scar is the ideal to validate scenarios like this? You may talk about this in another moment. So here's are the results of triggers model. Look, so there's 6 scenarios: A1, A2, A3, B1, B2, B3. The main difference here is like if you increase cohesion values, it's decrease the unstable areas. Triggers present us a result based on the safety factor, above 1 or under 1 value. This is another key issue about comparing one model to another. How each model present the results. So in this paper, the idea was the number of class presented by shell stub is different from triggers. So the idea was to divide in the middle the number of class of shell stub and compare with the triggers. But what you guys are seeing here, that in scenarios A1, A2, and A3, few variations were identified in the spatial distribution of susceptibility class. That is, as soil depth increased from 1 meter first scenario to 2 meters, the A3 scenarios, the unstable areas experienced a 10% increase. Between 2 meters A2 and 3 meters A3, the increase only 3%. Different geotechnical and hydrological parameters in scenarios B1, B2, and B3 result in important difference increase in the percentage of stable areas in 3 scenarios. And in scenario B1, 100% of the basin was classified as stable, as you can see here. So it's all blue. And in B2, 97%, and in B3, 87%. So in group B, the 3 scenarios had higher scar concentration class stability with only a few scars. In other words, we have a lot of stable cells associated with areas already affected. So in shell stub, one of the things that calls attention is the amount of red on the unconditional unstable areas in the first 3 scenarios. So Like the results of the triggers model, there was a strong similarity in the spatial distribution of susceptibility class for group A. The most significant change, an increase of nearly 10%, occurred between scenarios A1 and A2. And consider only the unconditional unstable class, the red one, the frequency, frequency is a parameter that was not present before, but is the distribution of the class along the watershed, has exactly the same percentage values as the unstable class of triggers. In other words, triggers in Schaustab present the same amount of unstable areas, lower than 1, as Schaustab present as the unconditionally unstable area. As I said before, the Schaustab, different from triggers, presents results that vary from unconditionally stable to unconditionally unstable. So it's a different idea that has a limit value, a critical value. In this paper, the idea was to consider, in order to compare the 4 lower classes and the 4 upper classes, the 3 upper classes. So this is an issue about comparing models that present the results in a different way. But in sum, both models perform similarly. When you verify the number of cells inside of the landslide scars. What brings us a question that triggers is it's a more detailed model. You can add more input values than Schaustab. Schaustab is, using the words of the authors, as a more simple model. So a more refined model compared to a more simple model gives somehow similar results. So going to the end, you can see here these 2 charts that compare the landslide potential of the 6 scenarios for each model. And our results present that both models shows to be effective in predicting shallow landslides to comparison of areas predicted to be unstable and locations mapped landslides considering the 2 parameters. So you can see here the values are quite similar, especially look at the scenario A1. You have a lot of the landslide potential presents somehow similar results. Difference in model performance between scenarios A and B to the difference of effective cohesion and soil thickness values can help evaluate appropriate values of geotechnical data to incorporate into regional susceptibility maps. This is one of the things that a lot of people talk about, which value to use as input data for models. Of course, nobody has all the values for every square meter in the terrain. So we are evaluating different papers and try to understand where the values are, in how similar they are in order to create these scenarios. But of course, would be a very great help if you could improve the understanding about the variation of some values in the terrain. Let's like the cohesion or the dynamic of the water in the soil. This could help understand better the spatial influence of these parameters in landslide susceptibility mapping. As I said before finishing here, there are 2 main issues we are discussing now. There are 2 data that we can add to the models, the digital elevation model and the landslide scar model. So what's the best digital elevation model to use in some sort of models? And how big should be my landslide scar in order to evaluate scenarios? Let's say if you map the landslide scar in the the rupture zone, the transport zone, and the deposit zone, your landslide scar will be very big. And the model will try to show where the rupture may occur. So depending how you map this, may give you a different results, not because the model is wrong, but because your approach about the validation method may not be suitable for some kind of test. And this brings us to another question: which resolution of DEM is best? Like, should we use a 90 meters DEM resolution, a spatial resolution raster, in order to map susceptibility in small watersheds? So there's some issues about the use of these models and the digital elevation models that we decide to apply in the test. As I said before, the equation of the models, we will not change it. We can just choose these two data, the landslide scar mapping and the DEM, and check the implications of this input data we decide to test, to use in order to test our scenarios. So guys, I hope I made myself understandable. My English is quite rusty. And again, I want to thank you all, especially Roberto, for this invitation. And here's my email. I'd be glad to answer any questions. Feel free to contact me. Roberto, thank you. This is the finish of my presentation.
Thank you, Dr. Martins. Thank you for preparing this presentation. It was very, very good. In fact, probably you know that I have cited this research paper many, many times. And yeah, let's check if there are questions in the chat. I am allowing the people if they want to write some of the questions. And thank you also, because it is very interesting to see the first part of the presentation, how those landslides were characterized, and to know specific things about those landslides in Brazil is very, very interesting. I think there are no questions. So
one of the things that is hard is how to map these landslides, because all the results are based on the landslide scar map. So you compare the raster to this, and we are seeing that there is no a clear method how to do it. And I assume in Colombia is the same. The rainforest take back its place and cover all the landslides. It's hard to identify where it occurs. So we rely on some photographs and satellite images, but it sometimes is not enough. We must do some field validation in order to separate, let's say, agriculture that you don't see in the image. And this is something that we are working on, and how to better map this data that is key for the validation approach. And I think this still is a question that we can't solve, especially in tropical terrain like our terrain. But I believe a remote sensing approach may give better answers for this issue.
Yeah, thank you. I think Dr. Johnny Vega has a question.
Yes, hi Roberto. How are you doing?
Are fine.
Excellent.
the limitation of triggers model. When you read the operational manual of triggers, you can see some limitations for steeped slopes. And the question is about how do you consider this limitation in your analysis and the uncertainties of your results?
Okay, I see. Oh, let me see how to address your question. Look, I think all methods have some sort of limitations. So we are perhaps we should think a different way to evaluate the results when comparing it with the landslide scar map, in order to understand better the limitations of each model. But like I said before, triggers, you can add more data when testing scenarios, Shellstab less data. But triggers give us more results, more outputs that we never test. Perhaps evaluating better these results, you can understand better these limitations that are present in the triggers idea. What I think about triggers, that because his face is not very friendly when you try to apply it, you must open a different tools. It's quite different from Shellstab. Few people are using it, especially in Brazil. So we somehow are not there yet to understand the limitations as you mentioned before. It's something that we must work on in the future to understand this association about the limitation, especially about the slopes, the inclination of the slopes and the results. But about the application of these models, I think sometimes there are sort of overused. They are overused, these models, because they are quite special Shellstab that are quite simple to apply. You can press some few buttons and you have the map. And I think we are not paying attention very well about exactly what you said, the limitations of everyone, not just triggers or each one. I mean, all those models were thought to be applied in a different terrain than ours in South America, with steep slopes, with a different vegetation cover. And I think we still need to go a little bit further to understand the lack of response of each model. The comparison may be a way, as I present here, a simpler model perform somehow with in the same way as a more refined model. But I think triggers are a little bit underestimated, because we have more results and you never, at least our group never go any further to understand this. When you compute triggers, the results come out, I think 6 or 7 rasters. So you used to, in order to compare with Shellstab, you consider only one. So there are other ones that we must think about. But triggers is a more tricky tool to use, and I think because of it, we don't know all the answers about its potential and limitations.
Thank you. Thank you, Tiago.
All right. Thank you. Thank you also for the question. And we are very happy to learn about what landslide in Brazil. And we are very happy to enjoy the presentation of Dr. Tiago Martins. Thank you so much for being here. I hope in a future occasion we can talk again and learn about what is your research in Brazil. So
okay.
Have a nice day and blessings.
Okay, thank you, Roberto. Was very kind of you to invite us, and I appreciate. And I hope maybe we'll meet one day. Thank you very much, and bye bye.
All right, bye bye. We are going to continue with the next presentation in just some minutes or even seconds. Then we are going to prepare for the streaming, and we will see you soon, very, very soon. All right, we are back again. It is a pleasure to have the last presentation of the Landslide Scientific Assessment Conference, Landslide Hazard. It is an honor to have Dr. Johnny Alexander Vega here with us. He is also I can tell him, a friend. He's going to present us quantitative risk assessment of landslides triggered by earthquakes and rainfall based on direct cost of urban buildings, a paper published in Geomorphology, but also about landslide risk and economic valuation in the northeastern zone of Medellin City. Those papers authored by Johnny Vega. So, hello, Johnny, how are you?
Pretty good, my friend Roberto. And you?
That's great. I am fine. Thank you. Thank you so much for inviting the direct invitation to present in this conference. And we want to know about your affiliation. I don't know anything we can know about your research, and then please you can start with your presentation. Thank you.
Okay, thank you so much. My name is Johnny Vega. I am a full-time professor in the University of Medellin. I am a civil engineer and master in geomatics, and I am a PhD student in the program of doctorate in engineering in the University of Medellin. I would like to talk with you. This is a brief summary of these two papers. A little bit of context. The study area is in Colombia, in the northwestern corner of South America, a country very susceptible to geodynamics processes by the convergence of several tectonic plates and the influence of the intertropical convergence zones with heavy rainfall patterns. Medellin is the center of the metropolitan area called Valle de Aburrá, and the risk analysis area is the northeastern zone of the city, where 35% of building damage and 74% of death by natural phenomena are landslide related. And this zone is characterized by informal construction or building of low-income neighborhoods without urban planning and seismic provisions. Is one of the purest area of the city. This is a panoramic view of the study area and an aerial view of the study area. In this area, almost 59% of the buildings are with unreinforced masonry. This is a particular zone with geomorphological condition of deposits of residual soils, several streams, a presence of local faults. In this slide, you can see the typical structures of the buildings. This is the workflow for landslide hazard assessment. This is a probabilistic approach that takes into account uncertainty modeling of geotechnical soil parameters and the uncertainty of the soil saturation because of rainfall. We use two conditions, static conditions related to the factor of safety and probability of failure, and a dynamic condition using the critical acceleration considering the PGA map. The result of this stage of the research is to obtain the annual probability of failures that you can see in this image. This is the workflow for physical vulnerability. For this stage of the research, we used the cadastral map and cadastral database. 5 building characteristics that were used: age, condition, number of stories, type of structural type, and the type of roof. And then the building were classified according to the HASUS classification using or simulate. We use to simulate 4 structural scenarios. Scenario number one was the original structure, material, and type. Scenario two consider all buildings in the zone built with masonry. The scenario three consider any structural type of a structure with a stiffness element, and the last structural scenario was the structural type with supporting walls with a stiffness element that fulfill the requirement of Colombian building codes. With this information, we generate vulnerability decision trees, and the final product of this stage was the physical vulnerability map. In this slide, you can see the quantitative risk assessment. In this stage of the research, we use the results of the previous stage, like a hazard, total probability of failure, and physical vulnerability index. And the economic losses for the building damage was carried out using a statistical method, specifically bootstrapping method. With this method, we can obtain different risk scenarios, and we can obtain different risk maps of the study zone. Which is the purpose for this risk map? Urban planning guidelines and urban planning strategies for reduction of the risks in the pure building and the pure neighborhood of the city. The implementation of the aforementioned workflows was thinking in different stages. The stage one, 6 years ago, was implemented in ArcGIS, Python, and model builder environment. The stage two of the implementation was developed in 2017 using Visual Studio, MapWinGIS, and Python. And the last year we did a last version of the software in completely open free source using QGIS and GDAL and Qt interfaces. The case study, more than 48,000 buildings in the communes 1, commune 2, and commune 3 in the northeastern zone of Medellin. You can see the structural material maps of these communes. We simulate the hazard and vulnerability for different values of horizontal ground acceleration, as you can see in this table, and we obtain the probable maximum economic loss for cells with a damage index higher than 50%. And also we estimate the potential loss in relation to vulnerability index for areas with pneumatic displacement higher than 5 centimeters. In this slide, you can see the risk maps, considering the magnitude of an earthquake according to the Colombian Building Code. And you can see in this part of the slide different simulations of according to the different scenarios that were considered. The line in blue color is the scenario with the original structure, material, and type, and the purple line is an assumed hypothetic scenario where structural types is supporting walls with a stiffness element that fulfills the requirement of Colombian Building Code. In this slide, you can see how the structural intervention of the building can produce a reduction by almost 21% in the total land risk. Hence, a structural modification in building is convenient to decrease the risk level at informal settlement in urban planning process. And it is noted that the improvement of the structural quality of building has a major effect on estimated damage costs. Even without the full implementation of the Colombian building codes from 2010, this cost may decrease between 0.5 million and 22 million of dollars, depending on the period of earthquake recurrence, according to horizontal ground acceleration. This is an example for a simulation that we made in 2016 in the Commune 3 Manrique. And then in 2017 occurred a landslide in this zone of within the cycle. The hazard was moderate and the vulnerability was high. If you combine the moderate or medium hazard with high vulnerability, you obtain a high risk level. And this is an example for the use of our methodology. And what about the conclusions? The economic losses in the study area caused by landslide induced by earthquake and rainfall are significant for ground acceleration higher than 0.3 Gs. In the case of lower acceleration, the affected areas are those with steeper slopes with pure quality housing construction, mostly wooden buildings. The proposed methodology can be used to obtain an estimate of the probable economic losses by earthquake and rainfall-induced landslides, taking into account the uncertainties of the building codes in the study zone. The methodology is a cost-effective approach and provides a basis for decision-making stage of urban planning process or urban planning strategies and the prioritization of areas requiring further studies using data obtained from secondary sources. This methodology allows different seismic and structural scenarios to be evaluated with the aim to define the most appropriate risk management strategies. The amount of investment required to reduce the risks of exposed buildings to an acceptable level of safety can be carried out through cost analysis following this methodology, and the proposed methodology may be transferable to areas with similar types of structure or similar structural systems. And thanks for your attention. This is the link for my ResearchGate profile. If you need to write me or mail me, do not hesitate to do it. And thanks.
Thank you, Dr. Johnny. Let me check if we have questions here in YouTube. Or please, if you have any questions, write them right now. We are grateful that you are accepted to present your research results here, your work. I know that you are working right now in other research. So let me ask you, what are you working right now? What are you doing in research?
Sorry, Roberto, are you talking to me?
Yeah, I asked you, well, I don't see any questions. I wanted that you shared with us what are you doing in your doctoral research?
Okay, yeah, of course. Currently, I am working in the topic of machine learning, deep learning. My doctoral research is about the evaluation of the impact of rainfall variability and climate change using explainable machine learning and deep learning, physical based model, and remote sensing data. This is the topic and the title, in fact, is the title of my doctoral research.
That's great. All right. Again, thank you for accepting this invitation. And I hope we can share with you in other scenarios, in other spaces in the future.
Absolutely, yes.
Thanks to all those who attended this conference. We have a lot of wonderful information to tell all those attendants to this event, probably in a future video that can be published or can be shared here in our channels or in the Facebook page. We are going to tell you about the numbers of this event. A lot of people has asked me about if we are going to give you what is the name? Like a diploma or a like a proof of the assistance to the conference. We are going to share with you the information about it via our website, the conference website. Many of you are interested in that. I am going to say that we had more than 880 registered participants. Many people attended only some of the conferences according to their possibilities, and it was a pleasure for us to share with you. And also even more or approximately 80 countries, people from 80 different countries, and probably all those numbers are going to be published even in a document that can be accessed by all of you in the future. Thank you so much for being part of the Landslide Scientific Assessment Conference. Thank you so much for your questions, your active participation. I hope you have learned a lot as I did. I want to thank a lot to the more than 35 speakers that participated in this event. It was voluntarily, they accepted a direct invitation we did to them. Also to the people that participated in the organizing committee of this event. I want to specifically thank to Johan Steven Mira. He's working the streaming and helping about all that was possible here and that you can see. Was a great contribution. Other people like the co-chair of this event, Julian Camilo Marin, also other organizers, Maria Fernanda Velázquez, Álvaro J. Matos, Oscar Sánchez, Ricardo Jaramillo, Camilo Fernández. I hope I don't miss any of the others. Derly Gomez. And yeah, thank you all for all what you did, your help. Finally, I want to invite you to share with us the purpose that we have as organization, LandScient. We want to do research, we want to facilitate, to make it easy or to do all what is possible for us to advance in the dissemination of knowledge but with the purpose of us, that is saving lives from natural hazards, from disasters. And I am sure that this event is something that is going in that direction. Thank you so much. We will see you in future conferences, events, or even in future spaces. May God bless you.
Bye, Roberto. See you next time.